here when we initialize the parameters manually, but because of the power of torch.nn, we have just passed it through the linear layer, which is going to perform some predefined forward computation in this layer. So this style of what's going on here is how you're going to see the majority of your PyTorch deep learning models created using pre-existing layers from the torch.nn module. So if we go back into torch.nn, we have a lot of different layers here. So we have convolutional layers, pooling layers, padding layers, normalization, recurrent, transformer, linear. We're using a linear layer, dropout, etc., etc. So for all of the common layers in deep learning, because that's what neural networks are, they're layers of different mathematical transformations, PyTorch has a lot of pre-built implementations. So that's a little bit of a sneaky trick that I've done to alter our model, but we've still got basically the exact same model as we had before. So what's next? Well, it's to train this model. So let's do that in the next video. Welcome back. So in the last video, we built a PyTorch linear model. Nice and simple, using a single nn.linear layer with one in feature, one out feature, and we overrid the forward method of nn.module using the linear layer that we created up here. So what's going to happen is when we do the forward pass on our model, we're going to put some data in and it's going to go through this linear layer, which behind the scenes, as we saw with torch nn linear, behind the scenes it's going to perform the linear regression formula here. So y equals x, a, t plus b. But in our case, we've got weight and bias. So let's go back. It's now time to write some training code. But before we do, let's set the model to use the target device. And so in our case, we've got a device of CUDA, but because we've written device agnostic code, if we didn't have access to a CUDA device, a GPU, our default device would be a CPU. So let's check the model device. We can do that first up here. Check the model current device, because we're going to use the GPU here, or we're going to write device agnostic code. That's better to say. Device agnostic code, that's the proper terminology. Device, what device are we currently using? This is the CPU, right? So by default, the model will end up on the CPU, but if we set it to model one call.to device, what do you think it's going to do now? If our current target device is CUDA, we've seen what to does in the fundamentals section. To is going to send the model to the GPU memory. So now let's check where the parameters of our model live, .device. If we send them to the device, previously it was the CPU. It's going to take a little bit longer while the GPU gets fired up and PyTorch goes, hey, I'm about to send you this model. You ready for it? Boom, there we go, wonderful. So now our model is on the device, or the target device, which is CUDA. And if CUDA wasn't available, the target device would be CPU, so this would just come out just exactly how we've got it here. But with that being said, now let's get on to some training code. And this is the fun part. What do we have to do? We've already seen this. For training, we're just going to clear up our workspace a little bit here. For training, we need, this is part of the PyTorch workflow, we need a loss function. What does a loss function do? It measures how wrong our model is. We need an optimizer. We need a training loop and a testing loop. And the optimizer, what does that do? Well, it optimizes the parameters of our model. So in our case, model1.stateDict, what do we have? So we have some parameters here. Within the linear layer, we have a weight and we have a bias. The optimizer is going to optimize these random parameters so that they hopefully reduce the loss function, which, remember, the loss function measures how wrong our model is. So in our case, because we're working with a regression problem, let's set up the loss function. And by the way, all of these steps are part of the workflow. We've got data ready. We've built or picked a model. We're using a linear model. Now we're up to here, 2.1, pick a loss function and an optimizer. We're going to do build a training loop in the same session because you know what? We're getting pretty darn good at this. Loss function equals what? Well, we're going to use L1 loss. So let's set that up. nn.L1 loss, which is the same as MAE. And if we wanted to set up our optimizer, What optimizer could we use? Well, PyTorch offers a lot of optimizers in torch.optim, SGD. That's stochastic gradient descent, because remember, gradient descent is the algorithm that optimizes our model parameters. Atom is another popular option. For now, we're going to stick with SGD. LR, which stands for learning rate. In other words, how big of a step will our optimizer change our parameters with every iteration? A smaller learning rate, such as 0.001, will be a small step, and then a large learning rate, such as 0.1, will be a larger step. Too big of a step, our model learns too much and it explodes. Too small of a step, our model never learns anything. But, we actually have to pass params first. I forgot about that. I got ahead of myself with the learning rate. Params is the parameters we'd like our optimizer to optimize. So in our case, it's model1.parameters because model1 is our current target model. Beautiful. So we've got a loss function and an optimizer. Now, let's write a training loop. So I'm going to set torch manual seed so we can try and get as reproducible as results as possible. Remember, if you get different numbers to what I'm getting, don't worry too much if they're not exactly the same. The direction is more important. So that means if my loss function is getting smaller, yours should be getting smaller too. Don't worry too much if your fourth decimal place isn't the same as what my values are. So we have a training loop ready to be written here. Epochs, how many should we do? Well, we did 200 last time. That worked pretty well, so let's do 200 again. Did you go through the extra curriculum yet? Did you watch the video for the unofficial PyTorch optimization loop song yet? This one here? Listen to the unofficial PyTorch optimization loop song. If not, it's okay. Let's sing it together. So for an epoch in range, epochs, we're going to go through the song in a second. We're going to set the model to train. In our case, it's model 1. Model to train. Now, step number 1 is what? Do the forward pass. This is where we calculate the predictions. So we calculate the predictions by passing the training data through our model. And in our case, because the forward method in model 1 implements the linear layer, this data is going to go through the linear layer, which is torch.nn.linear, and go through the linear regression formula. And then we calculate the loss, which is how wrong our model's predictions are. So the loss value equals loss fn, and here we're going to pass in ypred and ytrain. Then what do? We zero the optimizer, optimizer 0 grad, which because by default the optimizer is going to accumulate gradients behind the scenes, so every epoch we want to reduce those back to 0 so it starts from fresh. We're going to perform back propagation here. Back propagation by calling loss.backwards. If the forward pass goes forward through the network, the backward pass goes backwards through the network, calculating the gradients for the loss function with respect to each parameter in the model. So optimizer step, this next part, is going to look at those gradients and go, you know what, which way should I optimize the parameters? So because the optimizer is optimizing the model parameters, it's going to look at the loss and go, you know what, I'm going to adjust the weight to be increased, and I'm going to lower the bias and see if that reduces the loss. And then we can do testing. We can do both of these in the same hit. Now we are moving quite fast through this because we spent a whole bunch of time discussing what's going on here. So for testing, what do? We set the model into evaluation mode. That's going to turn off things like dropout and batch normalization layers. We don't have any of that in our model for now, but just it's good practice to always call eval whenever you're doing testing. And same with inference mode. We don't need to track gradients and a whole bunch of other things PyTorch does behind the scenes when we're testing or making predictions. So we use the inference mode context manager. This is where we're going to create test pred, which is going to be our test predictions, because here we're going to pass the test data features, forward pass through our model, and then we can calculate the test loss, which is our loss function, and we're going to compare the test pred to y-test. Wonderful. And then we can print out what's happening. So what should we print out? How about if epoch divided by 10 equals 0. So every 10 epochs, let's print something out. Print, we'll do an F string here. Epoch is epoch. And then we'll go loss, which is the training loss, can just be equal to the loss. And then we'll go test loss is equal to test loss. So do you think this will work? It's okay if you're not sure, but let's find out together, hey? Oh, we need a bracket there. Oh my goodness, what's going on? Runtime error. Expected all tensors to be on the same device. Oh, of course. Do you know what's happening here? But we found at least 2 devices, CUDA and CPU. Yes, of course, that's what's happened. So what have we done? Up here, we put our model on the GPU. But what's going on here? Our data, is our data on the GPU? No, it's not. By default, it's on the CPU. So we haven't written device agnostic code for our data. So let's write it here. Put data on the target device. Device agnostic code for data. So remember, one of the biggest issues with PyTorch, aside from shape errors, is that you should have your data or all of the things that you're computing with on the same device. So that's why if we set up device agnostic code for our model, we have to do the same for our data. So now let's put xtrain to device, ytrain equals ytrain to device. This is going to create device agnostic code. In our case, it's going to use CUDA because we have access to a CUDA device. But if we don't, this code will still work. It will still default to CPU. So this is good. I like that we got that error because that's just some of the things you're going to come across in practice, right? So now let's run this. What's happening here? Hey, look at that. Wonderful. So our loss starts up here, nice and high, and then it starts to go right down here for the training data, and then the same for the testing data. Beautiful. Right up here, and then all the way down. Okay, so this looks pretty good on the test data set. So how can we check this? How can we evaluate our model? Well, one way is to check its state dict. So state dict. What do we got here? What are our weight and bias? Oh my gosh, so close. So we just set weight and bias before to be 0.7 and 0.3. So this is what our model has estimated our parameters to be based on the training data. 0.6968, that's pretty close to 0.7, nearly perfect. And the same thing with the bias, 0.3025 versus the perfect value is 0.03. But remember, in practice, you won't necessarily know what the ideal parameters are. This is just to exemplify what our model is doing behind the scenes. It's moving towards some ideal representative parameters of whatever data we're working with. So in the next video, I'd like you to give it a go or before we get to the next video, make some predictions with our model and plot them on the original data. How close do the green dots match up with the red dots? And you can use this plot predictions formula or function that we've been using in the past. So give that a go, and I'll see you in the next video. But congratulations, look how quickly we just trained a model using the steps that we've covered in a bunch of videos so far, and device agnostic code. Oh, so good. I'll see you soon. In the last video, we did something very, very exciting. We worked through training an entire neural network. Some of these steps took us an hour or so worth of videos to go back through before, but we coded that in one video. So you ready to sing the song just to remind ourselves of what's going on? For an epoch in a range, call model.train, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. Let's test. Call model.eval with torch inference mode, do the forward pass, calculate the loss, print out what's happening. And then we do it again, again, for another epoch in a range. No, I'm kidding. We'll just leave it there. But that's the unofficial PyTorch optimization loop song. We created some device agnostic code so that we could make the calculations on the same device as what our model is, because the model's also using device agnostic code. And so now we've got to evaluate our model. So we've looked at the loss and the test loss here, and we know that our model's loss is going down, but what does this actually equate to when it makes predictions? That's what we're most interested in, right? And we've looked at the parameters. They're pretty close to the ideal parameters. So at the end of last video, I issued you the challenge to making and evaluating predictions, to make some predictions and plot them. I hope you gave it a shot. Let's see what it looks like together, hey? So turn the model into evaluation mode. Why? Because every time we're making predictions or inference, we want our model to be in eval mode. And every time we're training, we want our model to be in training mode. And then we're going to make predictions on the test data because we train on the trained data and we evaluate our model on the test data. Data that our model has never actually seen except for when it makes predictions. With Torch inference mode, we turn on inference mode whenever we make inference or predictions. So we're going to set ypreds equal to model1 and the test data goes in here. Let's have a look at what the ypreds look like. Wonderful. So we've got a tensor here. It shows us that they're still on the device CUDA. Why is that? Well, that's because previously we set the model 1 to the device, the target device. The same with the test data. So, subsequently, our predictions are also on the CUDA device. Now, let's bring in the plot predictions function here. So, check out our model predictions visually. We're going to adhere to the Data Explorer's motto of visualize, visualize, visualize. Plot predictions. And predictions are going to be set to equals ypreds. And let's have a look. How good do these look? Oh no. Oh, we got another error. Type error. Can't convert CUDA device type tensor to NumPy. Oh, of course. Look what we've done. So our plot predictions function, if we go back up, where did we define that? What does our plot predictions function use? It uses matplotlib, of course, and matplotlib works with NumPy, not PyTorch. And NumPy is CPU based. So, of course, we're running into another error down here because we just said that our predictions are on the CUDA device. They're not on the CPU, they're on a GPU. So, it's giving us this helpful information here. Use tensor.cpu to copy the tensor to host memory first. So, this is our tensor. Let's call .cpu and see what happens then. Is that going to go to CPU? Beautiful. Oh my goodness. Look at that. Look at that. Go the linear layer. The red dots, the predictions, are basically on top of the testing data. That is very exciting. Now again, you may not get the exact same numbers here, and that is perfectly fine, but the direction should be quite similar. So your red dots should be basically on top of the green dots, if not very slightly off, but that's okay. That's okay. We just want to focus on the direction here. So thanks to the power of backpropagation here and gradient descent, our model's random parameters have updated themselves to be as close as possible to the ideal parameters, and now the predictions are looking pretty darn good for what we're trying to predict. But we're not finished there. We've just finished training this model. What would happen if our notebook disconnected right now? Well, that wouldn't be ideal, would it? So, in the next part, we're going to move on to 6.5, saving and loading a trained model. So, I'm going to give you a challenge here as well, is to go ahead and go back and refer to this code here, saving a model in PyTorch, loading a PyTorch model, and see if you can save model 1, the state dictionary of model 1, and load it back in and get something similar to this. Give that a shot, and I'll see you in the next video. Welcome back. In the last video, we saw the power of the torch.nn.linear layer and backpropagation and gradient descent. And we got some pretty darn good predictions out of our model. So that's very exciting. Congratulations. You've now trained 2 machine learning models. Woohoo! But it's not over yet. We've got to save and load our trained model. So I issued you the challenge in the last video to try and save and load the model yourself. I hope you gave that a go. But we're going to do that together in this video. So we're going to start by importing path because we would like a file path to save our model to. And the first step we're going to do is create models directory. We don't have to recreate this because I believe we already have one, but I'm going to put the code here just for completeness. And this is just so if you didn't have a models directory, this would create one. So model path is going to go to path models, and then we'd like to model path.makedir. We're going to call makedir for make directory. We'll set parents equal to true, and if it exists, okay, that'll also be true, so we won't get an error. Oh my gosh, Google Colab, I didn't want that. We won't get an error if it already exists. And 2, we're going to create a model save path. So if you recall that PyTorch objects in general have the extension of what? This is a little pop quiz before we get to the end of this sentence. So this is going to be PyTorch workflow for this module that we're going through. This one here, chapter 01. PyTorch workflow model 1, and they usually have the extension .pt for PyTorch or PTH for PyTorch as well. I like PTH. But just remember, sometimes you might come across slightly different versions of that, PT or PTH. And we're going to create the model save name, or the save path. It's probably a better way to do it. Is going to be model path, and then we can use, because we're using the pathlib module from Python, we can save it under model name. And so if we look at this, what do we get? Model save path. We should get, oh, path is not defined. Oh, too many capitals here, Daniel. The reason why I'm doing these in capitals is because oftentimes hyperparameters, such as epochs in machine learning, are set as hyperparameters. LR could be learning rate, and then you could have as well model name equals yeah. But that's just a little bit of nomenclature trivia for later on. And model save path, we've done that. Now we're going to save the model state dictionary rather than the whole model. Save the model state dict, which you will find the pros and cons of in where? In the PyTorch documentation for saving and loading a model, which was a little bit of extra curriculum for a previous video. But let's have a look at our model save path. We'll print it out and we'll go torch save. We'll set the object that we're trying to save to equal model1.stateDict, which is going to contain our trained model parameters. We can inspect what's going on in here. StateDict. That'll show us our model parameters. Remember, because we're only using a single linear layer, we only have 2 parameters, but in practice, when you use a model with maybe hundreds of layers or tens of millions of parameters, viewing the StateDict explicitly like we are now might not be too viable of an option, but the principle still remains. A StateDict contains all of a model's trained or associated parameters and what state they're in. And the file path we're going to use is, of course, the model save path, which we've seen here is a POSIX path. Let's save our model. Wonderful, saving model to this file path here. And if we have a look at our folder, we should have 2 saved models now. Beautiful, 2 saved models. This one was from the workflow we did before up here, saving a model in PyTorch, loading a PyTorch model, and now the one we've got, of course, model 1 is the one that we've just saved. Beautiful. So now let's load a model. We're going to do both of these in one video. Load a PyTorch model. You know what? Because we've had a little bit of practice so far and we're going to pick up the pace. So let's go loaded. Let's call it, we'll create a new instance of loaded model 1, which is, of course, our linear regression model v2, which is the version 2 of our linear regression model class, which subclasses what? Subclasses nn.module. So if we go back here, up here to where we created it, so linear regression model v2 uses a linear layer rather than the previous iteration of linear regression model, which we created right up here. If we go up to here, which explicitly defined the parameters and then implemented a linear regression formula in the forward method. The difference between what we've got now is we use PyTorch's pre-built linear layer, and then we call that linear layer in the forward method, which is probably the far more popular way of building PyTorch models, is stacking together pre-built NN layers and then calling them in some way in the forward method. So let's load it in. So we'll create a new instance of linear regression model v2. And now what do? We've created a new instance. I'm just going to get out of this, make some space for us. We want to load the model state dict, the saved model1 state dict, which is the state dict that we just saved beforehand. So we can do this by going loaded model1, calling the load state dict method, and then passing it torch.load, and then the file path of where we saved that PyTorch object before. But the reason why we use the path lib is so that we can just call model save path in here. Wonderful. And then let's check out what's going on. Or actually, we need to put the target model or the loaded model to the device. The reason being is because we're doing all of our computing with device agnostic code. So let's send it to the device. And I think that'll be about it. Let's see if this works. Oh, there we go. Linear regression model v2. In features 1, out features 1, bias equals true. Wonderful. Let's check those parameters, hey? Next, loaded model1.parameters. Are they on the right device? Let's have a look. Beautiful. And let's just check the loaded state dictionary of loaded model1. Do we have the same values as we had previously? Yes, we do. Okay, so to conclusively make sure what's going on, let's evaluate the loaded model. Evaluate loaded model. Loaded model1, what do we do for making predictions, or what do we do to evaluate? We call .eval. And then if we're going to make some predictions, we use torch inference mode with torch inference mode, and then let's create loaded model1 preds equals loaded model 1, and we'll pass it the test data. And now let's check for equality between y preds, which is our previous model 1 preds that we made up here, y preds, and we're going to compare them to the fresh loaded model 1 preds. And should they be the same? Yes, they are. Beautiful. And we can see that they're both on the device CUDA. How amazing is that? So I want to give you a big congratulations because you've come such a long way. We've gone through the entire PyTorch workflow, from making data, preparing and loading it, to building a model, all of the steps that come in building a model. There's a whole bunch there. Making predictions, training a model. We spent a lot of time going through the training steps, but trust me, it's worth it because we're going to be using these exact steps all throughout the course. And in fact, you're going to be using these exact steps when you build PyTorch models after this course. And then we looked at how to save a model so we don't lose all our work. We looked at loading a model, and then we put it all together using the exact same problem, but in far less time. And as you'll see later on, we can actually make this even quicker by functionizing some of the code we've already written. But I'm going to save that for later. I'll see you in the next video where I'm just going to show you where you can find some exercises and all of the extra curriculum I've been talking about throughout this section 01 PyTorch workflow. I'll see you there. Welcome back. In the last video, we finished up putting things together by saving and loading our trained model, which is super exciting because that's come to the end of the PyTorch workflow section. So now this section is going to be exercises and extra curriculum, or better yet, where you can find them. So I'm going to turn this into Markdown, and I'm going to write here for exercises and extra curriculum, refer to. So within the book version of the course materials, which is at learnpytorch.io, we're in the 01 section, PyTorch Workflow Fundamentals. There'll be more here by the time you watch this video, likely. And then if we go down here, at the end of each of these sections, we've got the table of contents over here. We've got exercises and extra curriculum. I listed a bunch of things throughout this series of 01 videos, like what's gradient descent and what's backpropagation. So I've got plenty of resources to learn more on that. There's the loading and saving PyTorch documentation. There's the PyTorch cheat sheet. There's a great article by Jeremy Howard for a deeper understanding of what's going on in torch.nn. And there's, of course, the unofficial PyTorch optimization loop song by yours truly, which is a bit of fun. And here's some exercises. So the exercises here are all based on the code that we wrote throughout section 01. So there's nothing in the exercises that we haven't exactly covered, and if so, I'll be sure to put a note in the exercise itself. But we've got create a straight line data set using the linear regression formula, and then build a model by subclassing nn.module. So for these exercises, there's an exercise notebook template, which is of course linked here. And in the PyTorch Deep Learning GitHub, if we go into here, and then if we go into extras, and if we go into exercises, you'll find all of these templates here. They're numbered by the same section that we're in. This is PyTorch workflow exercises. So if you wanted to complete these exercises, you could click this notebook here, open in Google Colab. I'll just wait for this to load. There we go. And you can start to write some code here. You could save a copy of this in your own Google Drive and go through this. It's got some notes here on what you should be doing. You can, of course, refer to the text-based version of them. They're all here. And then if you want an example of what some solutions look like, now, please, I can't stress enough that I would highly, highly recommend trying the exercises yourself. You can use the book that we've got here. This is just all the code from the videos. You can use this. You can use, I've got so many notebooks here now. You can use all of the code that we've written here to try and complete the exercises, but please give them a go yourself. And then if you go back into the extras folder, you'll also find solutions. And this is just one example solutions for section 01, but I'm going to get out of that so you can't cheat and look at the solutions first. But there's a whole bunch of extra resources all contained within the PyTorch Deep Learning repo, extras, exercises, solutions, and they're also in the book version of the course. So I'm just going to link this in here. I'm going to put this right at the bottom here. Wonderful. But that is it. That is the end of the section 01 PyTorch workflow. So exciting. We went through basically all of the steps in a PyTorch workflow, getting data ready, turning it into tensors, build or pick a model, picking a loss function, on optimizer, we built a training loop, we fit the model to the data, we made a prediction, we evaluated our model, we improved through experimentation by training for more epochs, we'll do more of this later on, and we saved and reload our trained model. But that's going to finish 01. I will see you in the next section. Friends, welcome back. We've got another very exciting module. You ready? Neural network classification with PyTorch. Now, combining this module, once we get to the end, with the last one, which was regression. So remember, classification is predicting a thing, but we're going to see this in a second. And regression is predicting a number. Once we've covered this, we've covered two of the biggest problems in machine learning, predicting a number or predicting a thing. So let's start off with, before we get into any ideas or code, where can you get help? First things first is follow along with the code if you can. If in doubt, run the code. Try it for yourself. Write the code. I can't stress how important this is. If you're still stuck, press Shift, Command, and Space to read the doc string of any of the functions that we're running. If you are on Windows, it might be Control. I'm on a Mac, so I put Command here. If you're still stuck, search for your problem. If an error comes up, just copy and paste that into Google. That's what I do. You might come across resources like Stack Overflow or, of course, the PyTorch documentation. We'll be referring to this a lot again throughout this section. And then finally, oh wait, if you're still stuck, try again. If in doubt, run the code. And then finally, if you're still stuck, don't forget you can ask a question. The best place to do so will be on the course GitHub, which will be at the discussions page, which is linked here. If we load this up, there's nothing here yet because as I record these videos, the course hasn't launched yet, but press new discussion, talk about what you've got, problem with XYZ, leave a video number here and a timestamp, and that way we'll be able to help you out as best as possible. So video number, timestamp, and then your question here, and you can select Q&A. Finally, don't forget that this notebook that we're about to go through is based on Chapter 2 of the Zero to Mastery Learn PyTorch for Deep Learning, which is Neural Network Classification with PyTorch. All of the text-based code that we're about to write is here. That was a little spoiler. And don't forget, this is the home page, so my GitHub repo / PyTorch Deep Learning. For all of the course materials, everything you need will be here. So, that's very important. How can you get help? But this is the number one. Follow along with the code and try to write it yourself. Well, with that being said, when talking about classification, what is a classification problem? Now, as I said, classification is one of the main problems of machine learning. So you probably already deal with classification problems or machine learning powered classification problems every day. So let's have a look at some examples. Is this email spam or not spam? Did you check your emails this morning or last night or whenever? So chances are that there was some sort of machine learning model behind the scenes. It may have been a neural network, it may have not, that decided that some of your emails weren't spam. So to Daniel at mrdebug.com, hey Daniel, this deep learning course is incredible. I can't wait to use what I've learned. Oh, that's such a nice message. If you want to send that email directly to me, you can. That's my actual email address. But if you want to send me this email, well, hopefully my email, which is hosted by some email service, detects this as spam. Because although that is a lot of money and it would be very nice, I think if someone can't spell too well, are they really going to pay me this much money? So thank you, email provider, for classifying this as spam. And now, because this is one thing or another, not spam or spam, this is binary classification. So in this case, it might be 1 here, and this is a 0. So, or 0 or 1. So one thing or another. That's binary classification. If you can split it into one thing or another, binary classification. And then we have an example of, say we had the question, we asked our Photos app on our smartphone or whatever device you're using, is this photo of sushi, steak, or pizza? We wanted to search our photos for every time we've eaten sushi, or every time we've eaten steak, or every time we've eaten pizza. Far out, and this looks delicious. But this is multi-class classification. Now, why is this? Because we've got more than 2 things. We've got 1, 2, 3. And now this could be 10 different foods. It could be 100 different foods. It could be 1,000 different categories. So the ImageNet dataset, which is a popular dataset for computer vision, ImageNet, if we go to here, does it say 1,000 anywhere? 1K or 1,000? No, it doesn't. But if we go ImageNet 1K, download ImageNet data, maybe it's here. It won't say it, but you just, oh, there we go. 1,000 object classes. So this is multi-class classification because it has 1,000 classes. That's a lot, right? So that's multi-class classification, more than one thing or another. And finally, we might have multi-label classification, which is what tags should this article have? When I first got into machine learning, I got these two mixed up a whole bunch of times. Multi-class classification has multiple classes such as sushi, steak, pizza, but assigns one label to each. So this photo would be sushi in an ideal world, this is steak, and this is pizza. So one label to each. Whereas multi-label classification means you could have multiple different classes, but each of your target samples, such as this Wikipedia article, what tag should this article have? It may have more than one label. It might have 3 labels, it might have 10 labels. In fact, what if we went to the Wikipedia page for deep learning, Wikipedia, and does it have any labels? Oh, there we go. Where was that? I mean, you can try this yourself. This is just the Wikipedia page for deep learning. There is a lot. There we go. Categories: deep learning, artificial neural networks, artificial intelligence, and emerging technologies. So that is an example if we wanted to build a machine learning model to say, read all of the text in here and then go tell me what are the most relevant categories to this article. It might come up with something like these. In this case, because it has 1, 2, 3, 4, it has multiple labels rather than just one label of deep learning. It could be multi-label classification. So we'll go back, but there's a few more. These will get you quite far in the world of classification. And so let's dig a little deeper on binary versus multi-class classification. You may have already experienced this. So in my case, if I search on my phone in the Photos app for photos of a dog, it might come here. If I search for photos of a cat, it might come up with this. But if I wanted to train an algorithm to detect the difference between photos of, these are my 2 dogs. Aren't they cute? They're nice and tired and they're sleeping like a person. This is 7, number 7, that's her name, and this is Bella. This is a cat that me and my partner rescued. And so I'm not sure of what this cat's name is actually, so I'd love to give it a name, but I can't. So binary classification, if we wanted to build an algorithm, we wanted to feed it, say, 10,000 photos of dogs and 10,000 photos of cats, and then we wanted to find a random image on the internet and pass it through to our model and say, hey, is this a dog or is this a cat? It would be binary classification because the options are one thing or another, dog or cat. But then for multi-class classification, let's say we've been working on a farm and we've been taking some photos of chickens because they're groovy, right? Well, we updated our model and added some chicken photos in there. We would now be working with a multi-class classification problem because we've got more than one thing or another. So let's jump in to what we're going to cover. This is broadly, by the way, because this is just text on a page. You know, I like to just write code of what we're actually doing. So we're going to look at the architecture of a neural network classification model. We're going to check what the input shapes and output shapes of a classification model are, features and labels, in other words. Because remember, machine learning models, neural networks love to have numerical inputs, and those numerical inputs often come in tensors. Tensors have different shapes, depending on what data you're working with. We're going to see all of this in code. Creating custom data to view, fit, and predict on. We're going to go back through our steps in modeling. We covered this a fair bit in the previous section, but creating a model for neural network classification, it's a little bit different to what we've done, but not too outlandishly different. We're going to see how we can set up a loss function and an optimizer for a classification model. We'll recreate a training loop and evaluating loop or a testing loop. We'll see how we can save and load our models. We'll harness the power of nonlinearity. Wow, what does that even mean? Well, if you think of what a linear line is, what is that? It's a straight line. So you might be able to guess what a nonlinear line looks like. And then we'll look at different classification evaluation methods, so ways that we can evaluate our classification models. And how are we going to do all of this? Well, of course, we're going to be part cook, part chemist, part artist, part science, but for me, I personally prefer the cook side of things because we're going to be cooking up lots of code. So in the next video, before we get into coding, let's do a little bit more on what are some classification inputs and outputs. I'll see you there. Welcome back. In the last video, we had a little bit of a brief overview of what a classification problem is, but now let's start to get more hands-on by discussing what the actual inputs to a classification problem look like and the outputs look like. So let's say we had our beautiful food photos from before, and we were trying to build this app here called maybe Food Vision to understand what foods are in the photos that we take. And so what might this look like? Well, let's break it down to inputs, some kind of machine learning algorithm, and then outputs. In this case, the inputs, we want to numerically represent these images in some way, shape, or form. Then we want to build a machine learning algorithm. Hey, one might actually exist. We're going to see this later on in the transfer learning section for our problem. And then we want some sort of outputs. And in the case of Food Vision, we want to know, okay, this is a photo of sushi, and this is a photo of steak, and this is a photo of pizza. You could get more hands-on and technical and complicated, but we're just going to stick with single label, multi-class classification. So it could be a sushi photo, it could be a steak photo, or it could be a pizza photo. So how might we numerically represent these photos? Well, let's just say we had a function in our app that every photo that gets taken automatically gets resized into a square, into 224 width and 224 height. This is actually quite a common dimensionality for computer vision problems. And so we've got the width dimension, we've got the height, and then we've got this C here, which isn't immediately recognizable, but in the case of pictures, they often get represented by width, height, color channels. And the color channels is red, green, and blue, which is each pixel in this image has some value of red, green, or blue that makes whatever color is displayed here. And this is one way that we can numerically represent an image by taking its width, its height, and color channels, and whatever number makes up this particular image. We're going to see this later on when we work with computer vision problems. So we create a numerical encoding, which is the pixel values here. Then we input the pixel values of each of these images into a machine learning algorithm, which is often already exists. And if it doesn't exist for our particular problem, hey, well, we're learning the skills to build them now. We could use PyTorch to build a machine learning algorithm for this. And then outputs, what might these look like? Well, in this case, these are prediction probabilities, which the outputs of machine learning models are never actually discrete, which means it is definitely pizza. It will give some sort of probability value between 0 and 1. For, say, the closer to 1, the more confident our model is that it's going to be pizza. And the closer to 0 means that, hey, this photo of pizza, let's say this one, and we're trying to predict sushi, well, it doesn't think that it's sushi, so it's giving it quite a low value here. And then the same for steak, but it's really high, the value here, for pizza. We're going to see this hands-on, and then it's the opposite here, so it might have got this one wrong. But with more training and more data, we could probably improve this prediction. That's the whole idea of machine learning, is that if you adjust the algorithm, if you adjust the data, you can improve your predictions. And so, the ideal outputs that we have here, this is what our model's going to output. But for our case of building out food vision, we want to bring them back to, so we could just put all of these numbers on the screen here, but that's not really going to help people. We want to put out labels of what's going on here. So we can write code to transfer these prediction probabilities into these labels too. And so how did these labels come about? How do these predictions come about? Well, it comes from looking at lots of different samples. So this loop, we could keep going, improve these, find the ones where it's wrong, add more images here, train the model again, and then make our app better. And so if we want to look at this from a shape perspective, we want to create some tensors for an image classification example. So we're building food vision. We've got an image again. This is just reiterating on some of the things that we've discussed. We've got a width of 224 and a height of 224. This could be different. This could be 300, 300. This could be whatever values that you decide to use. Then we numerically encode it in some way, shape, or form. We use this as the inputs to our machine learning algorithm because what? Computers and machine learning algorithms, they love numbers. They can find patterns in here that we couldn't necessarily find, or maybe we could if you had a long enough time, but I'd rather write an algorithm to do it for me. Then it has some outputs, which comes in the form of prediction probabilities. The closer to 1, the more confident the model is in saying, hey, I'm pretty damn confident that this is a photo of sushi. I don't think it's a photo of steak, so I'm giving that 0. It might be a photo of pizza, but I don't really think so, so I'm giving it quite a low prediction probability. And so if we have a look at what the shapes are for our tensors here, if this doesn't make sense, don't worry. We're going to see the code to do all of this later on. But for now, we're just focusing on a classification input and output. The big takeaway from here is numerical encoding, outputs are numerical encoding, but we want to change these numerical codings from the outputs to something that we understand, say the word sushi. But this tensor may be batch size. We haven't seen what batch size is. That's all right, we're going to cover it. Color channels, width, height. So this is represented as a tensor of dimensions. It could be none here. None is a typical value for a batch size, which means it's blank. So when we use our model and we train it, all the code that we write with PyTorch will fill in this behind the scenes. And then we have 3 here, which is color channels. Then we have 224, which is the width. Then we have 224 as well, which is the height. Now, there is some debate in the field on the ordering. We're using an image as our particular example here on the ordering of these shapes. So say, for example, you might have height, width, color channels. Typically, width and height come together in this order, or they're just side by side in the tensor in terms of where the dimension appears. But color channels sometimes comes first. That means after the batch size or at the end here. But PyTorch, the default for now is color channels, width, height, though you can write code to change this order because tensors are quite flexible. And so, or the shape could be 32 for the batch size, 3, 224, 224, because 32 is a very common batch size, and you don't believe me? Well, let's go here. Yarn Lacoon, 32 batch size. Now, what is a batch size? Great tweet. Just keep this in mind for later on. Training with large mini batches is bad for your health. More importantly, it's bad for your test error. Friends don't let friends use mini batches larger than 32. So this is quite an old tweet. However, it still stands quite true because like today, it's 2022 when I'm recording these videos. There are batch sizes a lot larger than 32, but 32 works pretty darn well for a lot of problems. And so this means that if we go back to our slide, that if we use a batch size of 32, our machine learning algorithm looks at 32 images at a time. Now, why does it do this? Well, because sadly, our computers don't have infinite compute power. In an ideal world, we look at thousands of images at a time, but it turns out that using a multiple of 8 here is actually quite efficient. And so, if we have a look at the output shape here, why is it 3? Well, because we're working with 3 different classes. 1, 2, 3. So we've got shape equals 3. Now, of course, as you could imagine, these might change depending on the problem you're working with. So say if we just wanted to predict if a photo was a cat or a dog, we still might have this same representation here because this is the image representation. However, the shape here may be 2, or will be 2 because it's cat or dog, rather than 3 classes here. But a little bit confusing as well with binary classification. You could have the shape just being 1 here. But we're going to see this all hands-on. Just remember, the shapes vary with whatever problem you're working on. The principle of encoding your data as a numerical representation stays the same for the inputs, and the outputs will often be some form of prediction probability based on whatever class you're working with. So in the next video, right before we get into coding, let's just discuss the high-level architecture of a classification model. And remember, architecture is just like the schematic of what a neural network is. I'll see you there. Welcome back. In the last video, we saw some example classification inputs and outputs. The main takeaway that the inputs to a classification model, particularly a neural network, want to be some form of numerical representation. And the outputs are often some form of prediction probability. So let's discuss the typical architecture of a classification model. And hey, this is just going to be text on a page, but we're going to be building a fair few of these. So we've got some hyperparameters over here. We've got binary classification, and we've got multi-class classification. Now, there are some similarities between the two in terms of what problem we're working with, but there also are some differences here. And by the way, this has all come from, if we go to the book version of the course, we've got what is a classification problem, and we've got architecture of a classification neural network. So all of this text is available at learnpytorch.io and in section 2. So we come back. So the input layer shape, which is typically decided by the parameter in features, as you can see here, is the same of number of features. So if we were working on a problem such as we wanted to predict whether someone had heart disease or not, we might have 5 input features, such as 1 for age, a number for age, it might be, in my case, 28. Sex, could be male. Height, 180 centimeters. If I've been growing overnight, it's really closer to 177. Weight, well, it depends on how much I've eaten, but it's around about 75 kilos. And smoking status, which is 0. So it could be 0 or 1, because remember, we want numerical representation. So for sex, it could be 0 for males, 1 for female. Height could be its number. Weight could be its number as well. All of these numbers. Could be more, could be less as well. So this is really flexible, and it's a hyperparameter. Why? Because we decide the values for each of these. So in the case of our image prediction problem, we could have in features equals 3 for number of color channels. And then we go hidden layers. So there's the blue circle here. I forgot that this was all timed and colorful. But let's just discuss hidden layers. Each of these is a layer, nn.linear, nn.linear, nn.relu, nn.linear. So that's the kind of the syntax you'll see in PyTorch for a layer is nn.something. Now there are many different types of layers in this in PyTorch. If we go torch nn, basically everything in here is a layer in a neural network. And then if we look up what a neural network looks like, neural network, recall that all of these are different layers of some kind of mathematical operation. Input layer, hidden layer, you could have as many hidden layers as you want. Do we have ResNet architecture? The ResNet architecture, some of them have 50 layers. Look at this. Each one of these is a layer. And this is only the 34 layer version. I mean, there's ResNet 152, which is 152 layers. We're not at that yet, but we're working up the tools to get to that stage. Let's come back to here. The neurons per hidden layer. So we've got these out features, the green circle, the green square. Now, this is, if we go back to our neural network picture, this is Each one of these little things is a neuron, some sort of parameter. So if we had 100, what would that look like? Well, we'd have a fairly big graphic. So this is why I like to teach with code, because you could customize this as flexible as you want. So behind the scenes, PyTorch is going to create 100 of these little circles for us. And within each circle is what? Some sort of mathematical operation. So if we come back, what do we got next? Output layer shape. So this is how many output features we have. So in the case of binary classification is one class or the other. We're going to see this later on. Multi-class classification is you might have 3 output features, 1 per class, e.g. 1 for food, person, or dog if you're building a food, person, or dog image classification model. Hidden layer activation, which is, we haven't seen these yet, ReLU, which is a rectified linear unit, but can be many others because PyTorch, of course, has what? Has a lot of non-linear activations. We're going to see this later on. Remember, I'm kind of planting the seed here. We've seen what a linear line is, but I want you to imagine what a non-linear line is. It's going to be a bit of a superpower for our classification problem. What else do we have? Output activation. We haven't got that here, but we'll also see this later on, which could be sigmoid for, well, which is generally sigmoid for binary classification, but softmax for multi-class classification. A lot of these things are just names on a page. We haven't seen them yet. I like to teach them as we see them, but this is just a general overview of what we're going to cover. Loss function. What loss function, or what does a loss function do? It measures how wrong our model's predictions are compared to what the ideal predictions are. So for binary classification, we might use binary cross-entropy loss in PyTorch, and for multi-class classification, we might just use cross-entropy rather than binary cross-entropy. Get it? Binary classification, binary cross-entropy, and then optimizer. SGD, stochastic gradient descent. Oh, we've seen that one before. Another common option is the atom optimizer, and of course the torch.optim package has plenty more options. So this is an example multi-class classification problem, this network here. Why is that? And we haven't actually seen nn.sequential, but as you could imagine, sequential stands for it just goes through each of these steps. So multi-class classification because it has 3 output features, more than one thing or another. So 3 for food, person, or dog. But going back to our food vision problem, we could have the input as sushi, steak, or pizza. So we've got 3 output features, which would be 1 prediction probability per class of image. We have 3 classes, sushi, steak, or pizza. Now, I think we've done enough talking here and enough just pointing to text on slides. How about in the next video, let's code. I'll see you in Google Colab. Welcome back. Now, we've done enough theory of what a classification problem is, what the inputs and outputs are, and the typical architecture. Let's get in and write some code. So I'm going to get out of this and I'm going to go to colab.research.google.com so we can start writing some PyTorch code. I'm going to click New Notebook. We're going to start exactly from scratch. I'm going to name this section 2 and let's call it Neural Network Classification with PyTorch. I'm going to put underscore video because I'll just show you, you'll see this in the GitHub repo, but for all the video notebooks, the ones that I write code during these videos that you're watching, the exact code is going to be saved on the GitHub repo under video notebooks. So there's 00, which is the fundamentals, and there's the workflow underscore video. But the reference notebook with all the pretty pictures and stuff is in the main folder here. So PyTorch classification.ipynb. Oh, actually, maybe we'll just rename it that. PyTorch classification. But we know it's with neural networks. PyTorch classification. Okay, and let's go here. We'll add a nice title. So O2 neural network classification with PyTorch. And so we'll remind ourselves classification is a problem of predicting whether something is one thing or another. And there can be multiple things as the options, such as emails, spam or not spam, photos of dogs or cats, or pizza or sushi or steak. Lots of talk about food. And then I'm just going to link in here this resource, because this is the book version of the course. These are what the videos are based off. So book version of this notebook. And then all the resources are in here. All other resources in the GitHub, and then stuck. Ask a question here, which is under the discussions tab. We'll copy that in here. That way we've got everything linked and ready to go. But as always, what's our first step in our workflow? This is a little test, see if you remember. Well, it's data, of course, because all machine learning problems start with some form of data. We can't write a machine learning algorithm to learn patterns in data that doesn't exist. So let's do this video. We're going to make some data. Of course, you might start with some of your own that exists, but for now, we're going to focus on just the concepts around the workflow. So we're going to make our own custom data set. And to do so, I'll write the code first, and then I'll show you where I get it from. We're going to import the scikit-learn library. One of the beautiful things about Google Colab is that it has scikit-learn available. If you're not sure what scikit-learn is, it's a very popular machine learning library. PyTorch is mainly focused on deep learning, but scikit-learn is focused on a lot of things around machine learning. So Google Colab, thank you for having scikit-learn already installed for us. But we're going to import the make circles dataset, and rather than talk about what it does, let's see what it does. So make 1,000 samples. We're going to go n samples equals 1,000, and we're going to create circles. You might be wondering why circles. Well, we're going to see exactly why circles later on. So x and y, we're going to use this variable, how would you say, nomenclature, as capital X and Y. Why is that? Because X is typically a matrix, features, and labels. So let's go here, make circles, and we're going to make n samples, so 1,000 different samples. We're going to add some noise in there just for a little bit of randomness. Why not? You can increase this as you want. I found that 0.03 is fairly good for what we're doing. And then we're going to also pass in the random state variable, which is equivalent to setting a random seed. So we're flavoring the randomness here. Wonderful. So now let's have a look at the length of x, which should be what? And length of y. Oh, we don't have y underscore. Getting a bit trigger happy with this keyboard here. 1,000. So we have 1,000 samples of x with 1,000 or paired with 1,000 samples of y. Features, labels. So let's have a look at the first 5 of x. So print first 5 samples of x, and then we'll put in here x, and we can index on this 5, because we're adhering to the Data Explorer's motto of visualize, visualize, visualize. First 5 samples of y, and then we're going to go y. Same thing here. Wonderful. Let's have a look. Maybe we'll get a new line in here, just so looks a bit better. Wonderful. So, numerical. Our samples are already numerical. This is one of the reasons why we're creating our own data set. We'll see later on how we get non-numerical data into numbers, but for now, our data is numerical, which means we can learn it with our model, or we can build a model to learn patterns in here. So this sample has the label of 1, and this sample has the label of 1 as well. Now, how many features do we have per sample? If I highlight this line, how many features is this? It would make it a bit easier if there was a comma here, but we have 2 features of x, which relates to 1 label of y. And so far, we've only seen, let's have a look at all of y. We've got 0 and 1, so we've got 2 classes. What does this mean? 0 or 1, one thing or another. Well, it looks like binary classification to me, because we've got only 0 or only 1. If there was 0, 1, 2, it would be multi-class classification, because we have more than 2 things. So let's X out of this. Let's keep going and do a little bit more data exploration. So how about we make a data frame with pandas of circle data? There is truly no real definite way of how to explore data. For me, I like to visualize it multiple different ways, or even look at random samples in the case of large data sets such as images or text or whatnot. If you have 10 million samples, perhaps visualizing them one by one is not the best way to do so. So random can help you out there. So we're going to create a data frame and we can insert a dictionary here. So I'm going to call the features in this part of X, X1, and these are going to be X2. So let's write some code to index on this. So everything in the 0th index will be X1, and everything in the first index, there we go, will be X2. Let me clean up this code. This should be on different lines. Enter. And then we've got, let's put in the label as Y. So this is just a dictionary here. So X1 key to X0. X2, a little bit confusing because of 0 indexing, but X feature 1, X feature 2, and the label is Y. Let's see what this looks like. We'll look at the first 10 samples. Okay, beautiful. So we got X1, some numerical value, X2, another numerical value correlates to or matches up with label 0. But then this one, 0442208, and negative that number matches up with label 0. So I can't tell what the patterns are just looking at these numbers. You might be able to, but I definitely can't. We've got some ones. All these numbers look the same to me. So what can we do next? Well, how about we visualize, visualize, visualize? And instead of just numbers in a table, let's get graphical this time. Visualize, visualize, visualize. So we're going to bring in our friendly matplotlib, import matplotlib, which is a very powerful plotting library. I'm just going to add some cells here so we've got some space. Matplotlib.pyplot as PLT. That's right. We got this. Plot.scatter, we're going to do a scatter plot equals X, and we want the first index, and then Y is going to be X as well. So that's going to appear on the Y axis, and then we want to color it with the labels. We're going to see what this looks like in a second. And then the color map, CMAP stands for color map, is going to be plot.colormap, PLT, and then red, yellow, blue, one of my favorite color outputs. So let's see what this looks like. You ready? Ah, there we go. There's our circles. That's a lot better for me. So what do you think we're going to try and do here? If this is our data and we're working on classification, we're trying to predict if something is one thing or another. So our problem is we want to try and separate these two circles. So say given a number here, or given two numbers, an x1 and an x2, which are coordinates here, we want to predict the label. Is it going to be a blue dot or is it going to be a red dot? So we're working with binary classification. So we have one thing or another. Do we have a blue dot or a red dot? So this is going to be our toy data here. And a toy problem is, let me just write this down. This is a common thing that you'll also hear in machine learning. Note, the data we're working with is often referred to as a toy data set. A data set that is small enough to experiment on, but still sizable enough to practice the fundamentals. And that's what we're really after in this notebook, is to practice the fundamentals of neural network classification. So we've got a perfect data set to do this. And by the way, we got this from scikit-learn. So this little function here made all of these samples for us. And how could you find out more about this function here? Well, you could go scikit-learn, classification, data sets. There are actually a few more in here that we could have done. I just like the circle one. Toy data sets, we saw that. So this is like a toy box of different data sets. So if you'd like to learn more about some data sets that you can have a look in here and potentially practice on with neural networks or other forms of machine learning models from scikit-learn, check out this. Scikit-learn, I can't speak highly enough. I know this is a PyTorch course, we're not focused on this, but they kind of all come together in terms of the machine learning and deep learning world. You might use something from scikit-learn like we've done here to practice something, and then you might use PyTorch for something else like what we're doing here. Now, with that being said, what are the input and output shapes of our problem? Have a think about that, and also have a think about how we'd split this into training and test. So give those a go. We covered those concepts in some previous videos, but we'll do them together in the next video. I'll see you there. Welcome back. In the last video, we made some classification data so that we can practice building a neural network in PyTorch to separate the blue dots from the red dots. So let's keep pushing forward on that. And I'll just clean up here a little bit. But where are we in our workflow? What have we done so far? Well, we've got our data ready a little bit. We haven't turned it into tensors. So let's do that in this video, and then we'll keep pushing through all of these. So in here, I'm going to make this heading 1.1, check input and output shapes. The reason we're focused a lot on input and output shapes is why? Because machine learning deals a lot with numerical representations as tensors, and input and output shapes are some of the most common errors, like if you have a mismatch between your input and output shapes of a certain layer, of an output layer, you're going to run into a lot of errors there. So that's why it's good to get acquainted with whatever data you're using, what are the input shapes, and what are the output shapes you'd like. So in our case, we can go x.shape and y.shape. So we're working with NumPy arrays here. If we just look at x, that's what the make circles function has created for us. We've got an array, but as our workflow says, we'd like it in tensors. If we're working with PyTorch, we want our data to be represented as PyTorch tensors of that data type. And so we've got a shape here, we've got 1,000 samples, and x has 2 features, and y has no features. It's just a single number. It's a scalar, so it doesn't have a shape here. So there's 1,000 samples of y, 1,000 samples of x, 2 samples of x equals 1 y label. Now, if you're working with a larger problem, you might have 1,000 samples of x, but x is represented by 128 different numbers, or 200 numbers, or as high as you want, or just 10 or something like that. So just keep in mind that this number is quite flexible of how many features represent a label. Y is the label here. But let's keep going. So view the first example of features and labels. So let's make it explicit with what we've just been discussing. We'll write some code to do so. We'll get the first sample of x, which is the 0th index, and we'll get the first sample of y, which is also the 0th index. We could get really anyone because they're all of the same shape, but print values for one sample of x. What does this equal? X sample. And the same for y, which is y sample. And then we want to go print f string for one sample of x. We'll get the shape here. X sample.shape. And the same for y. And then we'll get y sample.shape. Beautiful. What's this going to do? Well, we've got one sample of x, so this sample here of these numbers, we've got a lot going on here. 75424 and 0231488074. I mean, you can try to find some patterns in those. If you do, all the best to you. And the same for y. So this is, we have the y sample, this correlates to a number 1, a label of 1. And then we have shapes for one sample of x, which is 2. So we have 2 features for y. It's a little bit confusing here because y is a scalar, which doesn't actually have a shape. It's just one value. So for me, in terms of speaking this, teaching it out loud, will be 2 features of x trying to predict one number for y. And so let's now create another heading, which is 1.2. Let's get our data into tensors. Turn data into tensors. We have to convert them from NumPy. And we also want to create train and test splits. Now, even though we're working with a toy data set here, the principle of turning data into tensors and creating train and test splits will stay around for almost any data set that you're working with. So let's see how we can do that. So we want to turn data into tensors, and for this we need to import torch. We'll get PyTorch and we'll check the torch version. It has to be at least 1.10. And I might just put this down in the next cell. Just make sure we can import PyTorch. There we go, 1.10 plus CUDA 111. If your version is higher than that, that is okay. The code below should still work, and if it doesn't, let me know. So x equals torch dot from numpy. Why are we doing this? Well, it's because x is a numpy array. And if we go x dot, does it have a D type attribute? Float 64. Can we just go type? Or maybe type. Oh, there we go. NumPy ND array. Can we just go type x? Oh, NumPy ND array. So we want it in a torch tensor. So we're going to go from NumPy. We saw this in the fundamentals section. And then we're going to change it into type torch.float. Float is an alias for float32. We could type the same thing. These two are equivalent. I'm just going to type torch float for writing less code. And then we're going to go the same with y, torch from numpy. Now, why do we turn it into a torch float? Well, that's because if you recall, the default type of numpy arrays is, if we go, might just put out this in a comma, x.dtype is float64. There we go. However, PyTorch, the default type is float32. So we're changing it into PyTorch's default type. Otherwise, if we didn't have this little section of code here, .type torch.float, our tensors would be of float64 as well. And that may cause errors later on. So we're just going for the default data type within PyTorch. And so now let's have a look at the first 5 values of x and the first 5 values of y. What do we have? Beautiful, we have tensor data types here. And now if we check the data type of x and we check the data type of y, what do we have? And then one more, I'm just going to type x. So we have our data into tensors. Wonderful. But now, so it's torch.tensor. Beautiful. But now we would like training and test sets. So let's go split data into training and test sets. And a very, very popular way to split data is a random split. So before I issued the challenge of how you would split this into a training and test set. So because these data points are kind of scattered all over the place, we could split them randomly. So let's see what that looks like. To do so, I'm going to use our faithful scikit-learn again. Remember how I said scikit-learn has a lot of beautiful methods and functions for a whole bunch of different machine learning purposes? Well, one of them is for a train test split. Oh my goodness, PyTorch, I didn't want autocorrect there. Train test split. Now you might be able to guess what this does. These videos are going to be a battle between me and Codelab's autocorrect. Sometimes it's good, other times it's not. So we're going to set this code up. I'm going to write it, or we're going to write it together. So we've got xtrain for our training features and xtest for our testing features. And then we also want our training labels and our testing labels. That order is the order that train test split works in. And then we have train test split. Now, if we wrote this function and we wanted to find out more, I can press Command Shift Space, which is what I just did, to have this. But truly, I don't have a great time reading all of this. You might, but for me, I just like going train test split. And possibly one of the first functions that appears, yes, is scikit-learn. How good is that? So scikit-learn.model-selection.train-test-split. Now, split arrays or matrices into random train and test subsets. Beautiful. We've got a code example of what's going on here. You can read what the different parameters do, but we're going to see them in action. This is just another example of where machine learning libraries such as scikit-learn, we've used matplotlib, we've used pandas, they all interact together to serve a great purpose. But now let's pass in our features and our labels. This is the order that they come in, by the way. Oh, and we have the returns splitting. So the order here, I've got the order, goes xtrain, xtest, ytrain, ytest. Took me a little while to remember this order, but once you've created enough train and test splits with this function, you kind of know this off by heart. So just remember features first, train first, and then labels. And we jump back in here. So I'm going to put in the test size parameter of 0.2. this is percentage-wise, so let me just write here, 0.2 equals 20% of data will be test, and 80% will be train. If we wanted to do a 50-50 split, that kind of split doesn't usually happen, but you could go 0.5. But the test size says, hey, how big in percentage-wise do you want your test data to be? And so behind the scenes, train test split will calculate what's 20% of our X and Y samples. So we'll see how many there is in a second. But let's also put a random state in here, because if you recall back in the documentation, train test split splits data randomly into random train and test subsets. And random state, what does that do for us? Well, this is a random seed, equivalent of, it's very similar to torch.manual seed. However, because we are using scikit-learn, setting torch.manual seed will only affect PyTorch code rather than scikit-learn code. So we do this so that we get similar random splits, as in I get a similar random split to what your random split is. And in fact, they should be exactly the same. So let's run this, and then we'll check the length of xtrain and length of xtest. So if we have 1,000 total samples, and I know that because above in our make circles function, we said we want 1,000 samples, that could be 10,000, that could be 100. That's the beauty of creating your own data set. And we have length ytrain. If we have 20% testing values, how many samples are going to be dedicated to the test sample? 20% of 1,000 is 200, and 80%, which is because training is going to be training here. So 100 minus 20% is 80%. So 80% of 1,000 is, let's find out. Run. Oh, beautiful. So we have 800 training samples, 200 testing samples. This is going to be the data set that we're going to be working with. So in the next video, we've now got training and test sets. We've started to move through our beautiful PyTorch workflow here. We've got our data ready. We've turned it into tensors. We've created a training and test split. Now it's time to build or pick a model. So I think we're still in the building phase. Let's do that in the next video. Welcome back. In the last video, we split our data into training and test sets. And because we did an 80-20 split, we've got about 800 samples to train on and 200 samples to test on. Remember, the training set is so that the model can learn patterns. Patterns that represent this data set here, the circles data set, red dots or blue dots. And the test data set is so that we can evaluate those patterns. And I took a little break before, but you can tell that because my notebook is disconnected. But if I wanted to reconnect it, what could I do? We can go here, runtime, run before. That's going to run all of the cells before. It shouldn't take too long because we haven't done any large computations, but this is good timing because we're up to part 2, building a model. And so there's a fair few steps here, but nothing that we haven't covered before. We're going to break it down. So let's build a model to classify our blue and red dots. And to do so, we want to tensors. I want 2, not tensors. That's all right. So let me just make some space here. There we go. So number 1, let's set up device agnostic code so we get in the habit of creating that. So our code will run on an accelerator. I can't even spell accelerator. Doesn't matter. You know what I mean. GPU, if there is one. 2, what should we do next? Well, we should construct a model, because if we want to build a model, we need a model. Construct a model, and we're going to go by subclassing nn.module. Now we saw this in the previous section. We subclassed nn.module. In fact, all models in PyTorch subclass nn.module. And let's go define loss function and optimizer. And finally, Google Colab's autocorrect is not ideal. And then we'll create a training and test loop. though this will probably be in the next section. We'll focus on building a model here. And of course, all of these steps are in line with what? They're in line with this. So we don't have device agnostic code here, but we're just going to do it enough so that we have a habit. These are the main steps. Pick or build a pre-trained model to suit your problem. Pick a loss function and optimizer. Build a training loop. So let's have a look. How can we start this off? So we'll import PyTorch and NN. We've already done this, but we're going to do it anyway for completeness, just in case you wanted to run your code from here. Import NN, and we're going to make device agnostic code. So we'll set the device equal to CUDA if torch.CUDA is available, else CPU, which will be the default. The CPU is the default. If there's no GPU, which means that CUDA is available, all of our PyTorch code will default to using the CPU. Device. Now, we haven't set up a GPU yet so far. You may have, but as you see, my target device is currently CPU. How about we set up a GPU? We can go into here, runtime, change runtime type, GPU, and I'm going to click save. Now, this is going to restart the runtime and reconnect. So once it reconnects, beautiful. We could actually just run this code cell here. This is going to set up the GPU device, but because we're only running this cell, if we were to just set up xtrain, we've not been defined. So because we restarted our runtime, let's run all, or we can just run before. So this is going to rerun all of these cells here. And do we have xtrain now? Let's have a look. Wonderful. Yes, we do. Okay, beautiful. So we've got device agnostic code. In the next video, let's get on to constructing a model. I'll see you there. Welcome back. In the last video, we set up some device agnostic code. So this is going to come in later on when we send our model to the target device and also our data to the target device. This is an important step because that way, if someone else were to run your code or you were to run your code in the future, because we've set it up to be device agnostic, by default, it will run on the CPU. But if there's an accelerator present, well, that means that it might go faster because it's using a GPU rather than just using a CPU. So we're up to step 2 here, construct a model by subclassing NN module. I think we're going to write a little bit of text here just to plan out the steps that we're doing. Now we've set up device agnostic code. Let's create a model so we're going to break it down. We've got some sub steps up here, but we're going to break it down, even this one down into some sub steps. So number 1 is we're going to subclass nn.module. And a reminder here, I want to make some space just so we're coding in about the middle of the page. So almost all models in PyTorch subclass nn.module because there's some great things that it does for us behind the scenes. And step 2 is we're going to create 2 nn.linear layers. And we want these that are capable to handle our data. So that are capable of handling the shapes of our data. Step 3, we want to defines a forward method. Why do we want to define a forward method? Well, because we're subclassing nn.module, right? And so the forward method defines a forward method that outlines the forward pass or forward computation of the model. And number 4, we want to instantiate, well, this doesn't really have to be the part of creating it, but we're going to do anyway. Instantiate an instance of our model class and send it to the target device. So going to be a couple of little different steps here, but nothing too dramatic that we haven't really covered before. So let's go number 1, construct a model that subclasses nn.module. So I'm going to code this all out. Well, we're going to code this all out together, and then we'll go back through and discuss it, and then maybe draw a few pictures or something to check out what's actually happening. So circle model v1, because we're going to try and split some circles. red and blue circles. This is our data up here. This is why it's called circle model, because we're trying to separate the blue and red circle using a neural network. So we've subclassed nn.module, and when we create a class in Python, we'll create a constructor here, init, and then put in super._init, and then inside the constructor, we're going to create our layers. So this is number 2, create 2 NN linear layers capable of handling the shapes of our data. So I'm going to write this down here. 2, create 2 NN.linear layers capable of handling the shapes of our data. And so if we have a look at xtrain, what are the shapes here? What's the input shape? Because xtrain is our features, right? And our features are going to go into our model. So we have 800 training samples. This is the first number here, of size 2 each. So 800 of these, and inside each is 2 numbers. Again, depending on the data set you're working with, your features may be 100 in length, a vector of 100, or it may be a different size tensor altogether, or there may be millions. It really depends on what data set you're working with. Because we're working with a simple data set, we're going to focus on that, but the principle's still the same. You need to define a neural network layer that is capable of handling your input features. So we're going to make layer 1 equals nn.linear. And then if we wanted to find out what's going on in nn.linear, we could run shift command space on my computer because it's a Mac, maybe shift control space if you're on Windows. So we're going to define the in features. What would in features be here? Well, we just decided that our x has 2 features, so our in features is going to be 2. And now what is the out features? This one is a little bit tricky. So in our case, we could have out features equal to 1 if we wanted to just pass a single linear layer, but we want to create 2 linear layers here. So why would out features be 1? Well, that's because if we have a look at the first sample of ytrain, we would want us to input, or maybe we'll look at the first 5. We want to map 1 sample of x to 1 sample of y, and y has a shape of 1. Or well, really it's nothing because it's a scalar, but we would still put 1 here so that it outputs just 1 number. But we're going to change this up. We're going to put it into 5, and we're going to create a second layer. Now, this is an important point of joining together neural networks. In features here, what do you think the in features of our second layer is going to be? If we've produced an out feature of 5 here, now this number is arbitrary. We could do 128, we could do 256. Generally it's multiples of 8, 64. We're just doing 5 now because we're keeping it nice and simple. We could do 8. Multiples of 8 is because of the efficiency of computing. I don't know enough about computer hardware to know exactly why that's the case, but that's just a rule of thumb in machine learning. So the in features here has to match up with the out features of a previous layer. Otherwise, we'll get shape mismatch errors. And so let's go here, out features. So we're going to treat this as the output layer. So this is the out features equals 1. So takes in 2 features and upscales to 5 features. So 5 numbers. So what this does, what this layer is going to do, is take in these 2 numbers of x, perform an n.linear. Let's have a look at what equation it does. An n.linear is going to perform this function here on the inputs. And it's going to upscale it to 5 features. Now, why would we do that? Well, the rule of thumb here, because this is denoted as a hidden unit, or how many hidden neurons there are, the rule of thumb is that the more hidden features there are, the more opportunity our model has to learn patterns in the data. So to begin with, it only has 2 numbers to learn patterns on, but if we upscale it to 5, it has 5 numbers to learn patterns on. Now, you might think, why don't we just go straight to like 10,000 or something? But there is like an upper limit here to sort of where the benefits start to trail off. We're just using 5 because it keeps it nice and simple. And then the in features of the next layer is 5 so that these 2 line up. We're going to map this out visually in a moment, but let's keep coding. We've got in features 2 for x, and now this is the output layer. So takes in 5 features from previous layer and outputs a single feature. And now this is same shape as y. So what is our next step? we want to define a forward method, a forward computation, a forward pass. So the forward method is going to define the forward computation, and as an input, it's going to take x, which is some form of data. And now here's where we can use layer 1 and layer 2. So now let's just go return, or we'll put a note here of what we're doing. 3, we're going to go define a forward method that outlines the forward pass. So forward, and we're going to return, and here's some notation we haven't quite seen yet. And then we're going to go self layer 2, and inside the brackets we'll have self layer 1. Inside those brackets we're going to have x. So the way this goes is x goes into layer 1, and then the output of layer 1 goes into layer 2. So whatever data we have, so our training data, xtrain, goes into layer 1, performs the linear calculation here, and then it goes into layer 2, and then layer 2 is going to go to the output. So x is the input, layer 1, computation, layer 2, output. So we've done that. Now let's do step 4, which is instantiate an instance of our model class and send it to the target device. So this is our model class, circle model v0. We're just going to create a model because it's the first model we've created of this section. Let's call it model 0, and we're going to go circle model v1, and then we're going to go .2, and we're going to pass in device because that's our target device. Let's now have a look at model 0, and then, oh, typo? Yep, classic. What did we get wrong here? Oh, did we not pass in self? Self, oh, there we go. Little typo, classic. But the beautiful thing about creating a class here is that we could put this into a Python file, such as model.py, and then we wouldn't necessarily have to rewrite this all the time. We could just call it. And so let's just check what device it's on. So target device is CUDA because we've got a GPU. Thank you, Google Colab. And then if we wanted to, let's go next model 0 dot parameters. We'll call the parameters, and then we'll go device. CUDA. Beautiful. So that means our model's parameters are on the CUDA device. Now, we've covered enough code in here for this video. So if you want to understand it a little bit more, go back through it. But we're going to come back in the next video and make it a little bit more visual. So I'll see you there. Welcome back. In the last video, we did something very, very exciting. We created our first multi-layer neural network. But right now, this is just code on a page. But truly, this is what the majority of building machine learning models in PyTorch is going to look like. You're going to create some layers, or as simple or as complex as you like. And then you're going to use those layers in some form of forward computation to create the forward pass. So let's make this a little bit more visual. If we go over to the TensorFlow playground, and now TensorFlow is another deep learning framework similar to PyTorch. It just allows you to write code such as this to build neural networks, fit them to some sort of data to find patterns in data, and then use those machine learning models in your applications. But let's create this. Oh, by the way, this is playground.tensorflow.org. This is a neural network that we can train in the browser if we really wanted to. So that's pretty darn cool. But we've got a data set here, which is kind of similar to the data set that we're working with. If we have a look at our circles one, let's just say it's close enough. It's circular, that's what we're after. But if we increase this, we've got 5 neurons now. We've got 2 features here, x1 and x2. Where is this reminding you of what's happening? There's a lot of things going on here that we haven't covered yet, but don't worry too much. We're just focused on this neural network here. So we've got some features as the input. We've got 5 hidden units. This is exactly what's going on with the model that we just built. We pass in x1 and x2, our values. So if we go back to our data set, these are x1 and x2. We pass those in. So we've got 2 input features. And then we pass them to a hidden layer, a single hidden layer, with 5 neurons. What have we just built? If we come down into here, to our model, we've got in features 2, out features 5. And then that feeds into another layer which has in features 5 and out features 1. So this is the exact same model that we've built here. Now, if we just turn this back to linear activation, because we're sticking with linear for now, we'll have a look at different forms of activation functions later on. And maybe we put the learning rate, we've seen the learning rate to 0.01. We've got epochs here, got classification, and we're going to try and fit this neural network to this data. Let's see what happens. Oh, the test loss, it's sitting about halfway, 0.5. So about 50% loss. So if we only have 2 classes and we've got a loss of 50%, what does that mean? Well, if the perfect loss was 0 and the worst loss was 1, then we just divide 1 by 2 and get 50%, but we've only got 2 classes. So that means if our model was just randomly guessing, it would get a loss of about 0.5, because you could just randomly guess whatever data point belongs to blue or orange in this case. So in a binary classification problem, if you have the same number of samples in each class, in this case, blue dots and orange dots, randomly guessing will get you about 50%, just like tossing a coin. Toss a coin 100 times and you get about 50-50. Might be a little bit different, but it's around about that over the long term. So we've just fit for 3,000 epochs, and we're still not getting any better loss. I wonder if that's going to be the case for our neural network. And so to draw this in a different way, I'm going to come to a little tool called FigJam, which is just a whiteboard that we can put shapes on, and it's based in the browser. So this is going to be nothing fancy. It's going to be a simple diagram. Say this is our input, and I'm going to make this green because my favorite color is green. And then we're going to have, let's make some different colored dots. I want a blue dot here. So this can be dot 1 and dot 2. I'll put another dot here. I'll zoom out a little so we have a bit more space. Or maybe that was too much. 50% looks all right. So let me just move this around. Might move these up a little. So we're building a neural network here. This is exactly what we just built. And so we go here. Or maybe we'll put this as input x1. So this will make a little bit more sense. And then maybe we can copy this. Now this is x2. And then we have some form of output. Let's make this one. And we're going to color this orange. So output. Right. So you can imagine, have we got connected dots here? Maybe we'll connect these. So our inputs are going to go through all of these. I wonder if I can draw here. Okay, this is going to be a little bit more complex, but that's all right. So this is what we've done. We've got 2 input features here. And if we wanted to keep drawing these, we could. All of these input features are going to go through all of these hidden units that we have. I just drew the same arrow twice. That's okay. But this is what's happening in the forward computation method. It can be a little bit confusing for when we coded it out. Why is that? Well, from here, it looks like we've only got an input layer into a single hidden layer in the blue and an output layer. But truly, this is the same exact shape. You get the point. And then all of these go to the output. But we're going to see this computationally later on. So whatever data set you're working with, you're going to have to manufacture some form of input layer. Now, this may be, you might have 10 of these if you have 10 features, or 4 of them if you have 4 features. And then if you wanted to adjust these, well, you could increase the number of hidden units or the number of out features of a layer. What just has to match up is that the layer it's going into has to have a similar shape as what's coming out of here. So just keep that in mind as you're going on. And in our case, we only have one output, so we have the output here, which is y. So this is a visual version. We've got the TensorFlow playground. You could play around with that. You can change this to increase. Maybe you want 5 hidden layers with 5 neurons in each. This is a fun way to explore. This is a challenge, actually. Go to playground.tensorflow.org, replicate this network, and see if it fits on this type of data. What do you think? Will it? Well, we're going to have to find out in the next few videos. So I'm going to show you in the next video another way to create the network that we just created. This one here, with even less code than what we've done before. I'll see you there. Welcome back. In the last video, we discussed, well actually in the previous video to last, we coded up this neural network here, circle model v0. By subclassing nn.module, we created two linear layers, which are capable of handling the shape of our data. In features 2, because why? We have 2x features. Out features, we're upscaling the 2 features to 5, so that it gives our network more of a chance to learn. And then, because we've upscaled it to 5 features, the next subsequent layer has to be able to handle 5 features as input, and then we have 1 output feature because that's the same shape as our Y here. Then we got a little bit visual by using the TensorFlow playground. Did you try out that challenge? Make 5 hidden layers with 5 neurons? Did it work? And then we also got a little bit visual in Figma as well. This is just another way of visualizing different things. You might have to do this a fair few times when you first start with neural networks, but once you get a bit of practice, you can start to infer what's going on through just pure code. So now let's keep pushing forward. How about we replicate this with a simpler way? Because our network is quite simple, that means it only has 2 layers. That means we can use, let's replicate the model above using nn.sequential. And I'm going to code this out and then we can look up what nn sequential is, but I think you'll be able to comprehend what's happening by just looking at it. So nn, which is torch.nn, we can do torch.nn, but we've already imported nn. We're going to call nn.sequential, and then we're going to go nn.linear. And what was the in features of our nn.linear? Well, it was 2 because we have 2 in features. And then we're going to replicate the same out features. Remember, we could customize this to whatever we want. 10, 100, 128. I'm going to keep it at 5, nice and simple. And then we go nn.linear. And the in features of this next layer is going to be 5 because the out features of the previous layer was 5. And then finally, the out features here is going to be 1 because we want 1 y value to our 2x features. And then I'm going to send that to the device. And then I'm going to have a look at model 0. So this is of course going to override our previous model 0, but have a look. The only thing different is that this is from the circle model v0 class. We subclassed nn.module, and the only difference is the name here. This is just from sequential. And so, can you see what's going on here? So as you might have guessed, sequential, it implements most of this code for us behind the scenes. Because we've told it that it's going to be sequential, it's just going to go, hey, step the code through this layer, and then step the code through this layer. It outputs basically the same model, rather than us creating our own forward method. And you might be thinking, Daniel, why didn't you show us this earlier? That looks like such an easy way to create a neural network compared to this. Well, yes, you're 100% right. That is an easier way to create a neural network. However, the benefit of subclassing, and that's why I started from here, is that when you have more complex operations, such as things you'd like to construct in here, and a more complex forward pass, it's important to know how to build your own subclasses of nn.module. But for simple, straightforward, stepping through each layer one by one, so this layer first, and then this layer, you can use nn.sequential. In fact, we could move this code up into here. So we could do this, self dot, we'll call this 2 linear layers equals nn.sequential. And we could have layer 1, and we could go self.layer1, and, or actually, we'll just recode it. We'll go nn.linear, so it's the same code as what we've got below. In features, if I could type, that'd be great. In features equals 2, out features equals 5, and then we go nn.linear, and then we go in features equals what? Equals 5 because it has to line up. Out features equals 1. And then we've got 2 linear layers, and then if we wanted to get rid of this, return 2 linear layers, and we'll pass it x. We'll remake it. There we go. Well, because we've created these as well, let's get rid of that. Beautiful. So that's the exact same model, but just using nn.sequential. Now I'm going to get rid of this so that our code is not too verbose. That means a lot going on, but this is the flexibility of PyTorch. So just keep in mind that there's a fair few ways to make a model. The simplest is probably sequential, and then subclassing this is a little bit more complicated than what we've got, but this can extend to handle a lot more complex neural networks, which you'll likely have to be building later on. So let's keep pushing forward. Let's see what happens if we pass some data through here. So we'll just rerun this cell to make sure we've got our model 0 instantiated. We'll make some predictions with the model. So of course, if we have a look at our model 0.stateDict, oh, this will be a good experiment. So look at this. So we have weight, a weight tensor, a bias tensor, a weight tensor, and a bias tensor. So this is for the first of the 0th layer, these two here with the 0 dot, and then the 1 dot weight is for, of course, the first index layer. Now have a look inside here. Now you see how out features is 5? Well, that's why our bias parameter has 5 values here. And the same thing for this weight value here. And the weight value here, why does this have 10 samples? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because 2 times 5 equals 10. So this is just with a simple 2-layer network. Look at all the numbers that are going on behind the scenes. Imagine coding all of these by hand. Like there's something like 20 numbers or something here. Now we've only done 2 layers here. Now the beauty of this is that in the previous section, we created all of the weight and biases using nn.parameter and random values. You'll notice that these are all random too. Again, if yours are different to mine, don't worry too much because they're going to be started randomly and we haven't set a random seed. But the thing to note here is that PyTorch is creating all of these parameters for us behind the scenes. And now when we do backpropagation and gradient descent, when we code our training loop, the optimizer is going to change all of these values ever so slightly to try and better fit or better represent the data so that we can split our 2 circles. And so you can imagine how verbose this could get if we had, say, 50 layers with 128 different features of each. So let's change this up, see what happens. Watch how quickly the numbers get out of hand. Look at that. We just changed one value and look how many parameters our model has. So you might be able to calculate that by hand, but I personally don't want to. So we're going to let PyTorch take care of a lot of that for us behind the scenes. So for now, we're keeping it simple, but that's how we can crack our models open and have a look at what's going on. Now that was a little detour. It's time to make some predictions with random numbers. I just wanted to highlight the fact that our model is in fact instantiated with random numbers here. So the untrained preds, model 0, we're going to pass in xtest, and of course, we have to send the test data to the device. Otherwise, if it's on a different device, we'll get errors because PyTorch likes to make calculations on the same device. So we'll go print. Let's do a nice print statement of length of predictions. We're going to go length or len untrained preds. We'll pass that in there. And then we'll go, oh no, we need a squiggle. And then we'll go shape. Shape is going to be untrained preds.shape. So this is again following the Data Explorer's motto of visualize, visualize, visualize. And sometimes print is one of the best ways to do so. So length of test samples. You might already know this, or we've already checked this together, haven't we? Xtest. And then we're going to get the shape, which is going to be xtest.shape. Wonderful. And then we're going to print. What's our little error here? Oh no. Colab's tricking me. So let's go first 10 predictions. And we're going to go untrained preds. So how do you think these predictions will fare? They're doing it with random numbers. And what are we trying to predict again? Well, we're trying to predict whether a dot is a red dot or a blue dot or 0 or 1. And then we'll go first 10 labels is going to be, we'll get this on the next line, and we'll go y test. Beautiful. So let's have a look at this. Untrained predictions. So we have length of predictions is 200. Length of test samples is 200, but the shapes are different. What's going on here? Y test, and let's have a look at X test. Oh, well, I better just have a look at Y test. Why do we have a 2 there? Oh, I've done X test dot shape. Oh, that's test samples. That's okay. And then the predictions are 1. Oh, yes. So Y test, let's just check the first 10. X test. So a little bit of clarification needed here with your shapes. So maybe we'll get this over here because I like to do features first and then labels. What did we miss here? Oh, X test 10 and Y test. See, we're troubleshooting on the fly here. This is what you're going to do with a lot of your code. So there's our test values, there's the ideal labels, but our predictions, they don't look like our labels. What's going on here? We can see that they're on the CUDA device, which is good. We set that. We can see that they got gradient tracking. Oh, we didn't with Torch, we didn't do inference mode here. That's a poor habit of us, excuse me. Let's inference mode this. There we go. So you notice that the gradient tracking goes away there. And so our predictions are nowhere near what our test labels are, but also they're not even in the same like ballpark. Like these are whole numbers, 1 or 0, and these are all floats between 1 and 0. So maybe rounding them, will that do something? So where's our preds here? So we go torch.round. What happens there? Oh, they're all 0. Well, our model's probably going to get about 50% accuracy. Why is that? Because all the predictions look like they're going to be 0. And they've only got 2 options, basically head or tails. So, when we create our model and when we evaluate it, we want our predictions to be in the same format as our labels. But we're going to cover some steps that we can take to do that in a second. What's important to take away from this is that there's another way to replicate the model we've made above using nn.sequential. We've just replicated the same model as what we've got here. nn.sequential is a simpler way of creating a PyTorch model, but it's limited because it literally just sequentially steps through each layer in order. Whereas in here, you can get as creative as you want with the forward computation. And then inside our model, PyTorch has behind the scenes created us some weight and bias tensors for each of our layers with regards to the shapes that we've set. And so the handy thing about this is that if we got quite ridiculous with our layers, PyTorch would still do the same thing behind the scenes, create a whole bunch of random numbers for us. And because our numbers are random, it looks like our model isn't making very good predictions. But we're going to fix this in the next few videos when we move on to fitting the model to the data and making a prediction. But before we do that, we need to pick a loss function and an optimizer and build a training loop. So let's get on to these two things. Welcome back. So over the past few videos, we've been setting up a classification model to deal with our specific shape of data. Now recall, depending on the data set that you're working with, will depend on what layers you use. For now, we're keeping it simple. nn.linear is one of the most simple layers in PyTorch. We've got 2 input features. We're upscaling that to 5 output features. So we have 5 hidden units, and then we have 1 output feature. And that's in line with the shape of our data. So 2 features of X equals 1 number for Y. So now let's continue on modeling with where we're up to. We have build or pick a model. So we've built a model. Now we need to pick a loss function and optimizer. We're getting good at this. So let's go here, set up loss function and optimizer. Now here comes the question. If we're working on classification, previously we used, let's go to the next one, nn.l1 loss for regression, which is MAE, mean absolute error. But just a heads up, that won't necessarily work with a classification problem. So which loss function or optimizer should you use? So again, this is problem specific, but with a little bit of practice, you'll get used to using different ones. So for example, for regression, you might want, which is regression's predicting a number. And I know it can get confusing because it looks like we're predicting a number here. We are essentially predicting a number, but this relates to a class. So for regression, you might want MAE or MSE. which is mean absolute error, or mean squared error. And for classification, you might want binary cross entropy or categorical cross entropy, which is sometimes just referred to as cross entropy. Now, where would you find these things out? Well, through the internet, of course. So you could go, what is binary cross entropy? I'm going to leave you this for your extra curriculum to read through this. We've got a fair few resources here. Understanding binary cross entropy / log loss by Daniel Godoy. Oh, yes. Great first name, my friend. This is actually the article that I would recommend too if you want to learn what's going on behind the scenes through binary cross entropy. For now, there's a lot of math there. We're going to be writing code to implement this. So PyTorch has done this for us. Essentially, what does a loss function do? Let's remind ourselves. Go down here. As a reminder, the loss function measures how wrong your model's predictions are. So I'm also going to leave a reference here to, I've got a little table here in the book version of this course, so 0.2 neural network classification with PyTorch, setup, loss function, and optimizer. So we've got some example loss functions and optimizers here, such as stochastic gradient descent or SGD optimizer. Atom optimizer is also very popular. So I've got problem type here, and then the PyTorch code that we can implement this with. We've got binary cross entropy loss. We've got cross entropy loss, mean absolute error, MAE, mean squared error, MSE. So you want to use these two for regression. There are other different loss functions you could use, but these are some of the most common. That's what I'm focusing on, the most common ones that are going to get you through a fair few problems. We've got binary classification, multi-class classification. What are we working with? We're working with binary classification, so we're going to look at torch.nn, BCE, which stands for binary cross entropy, loss with logits. What the hell is a logit? And BCE loss. Now, this is confusing, and trust me, when I first started using PyTorch, I got a little bit confused about why they have two here, but we're going to explore that anyway. So, what is a logit? So, if you search what is a logit, you'll get this, and you get statistics, and you get the log odds formula. In fact, if you want to read more, I would highly encourage it. So you could go through all of this. We're going to practice writing code for it instead. Luckily, PyTorch does this for us. But logit is kind of confusing in deep learning. So if we go, what is a logit in deep learning? It kind of means a different thing. It's kind of just a name of what... Yeah, there we go. What is the word logits in TensorFlow? As I said, TensorFlow is another deep learning framework. So let's close this. What do we got? We got a whole bunch of definitions here. Logits layer. Yeah, this is one of my favorites. In context of deep learning, the logits layer means the layer that feeds into the softmax. So softmax is a form of activation. We're going to see all of this later on because this is just words on a page right now. Softmax or other such normalization. So the output of the softmax are the probabilities for the classification task, and its input is the logits layer. Whoa, there's a lot going on here. So let's just take a step back and get into writing some code. And for optimizers, I'm just going to complete this. And for optimizers, two of the most common and useful are SGD and Atom. However, PyTorch has many built-in options. And as you start to learn more about the world of machine learning, you'll find that if you go to torch.optim or torch.nn, so if we have .nn, what do we have in here? Loss functions. There we go. Beautiful. That's what we're after. L1 loss, which is MAE, MSE loss, cross entropy loss, CTC loss. All of these different types of loss here will depend on the problem you're working on, but I'm here to tell you that for regression and classification, two of the most common of these. See, this is that confusion again. BCE loss, BCE with logits loss. What the hell is a logit? My goodness. Okay, that's enough. And optim, these are different optimizers. We've got probably a dozen or so here, algorithms. Ada delta, ada grad, atom W. This can be pretty full on when you first get started, but for now, just stick with SGD and the atom optimizer. They're two of the most common. Again, they may not perform the best on every single problem, but they will get you fairly far just knowing those, and then you'll pick up some of these extra ones as you go. But let's just get rid of all of, so I'll put this in here, this link. So we'll create our loss function. For the loss function, we're going to use torch.nn.bce with logits loss. Woohoo! This is exciting. For more on what binary cross entropy, which is BCE, a lot of abbreviations in machine learning and deep learning is, check out this article. And then for a definition on what a logit is, we're going to see a logit in a second in deep learning, because again, deep learning is one of those fields of machine learning which likes to be a bit rebellious, likes to be a bit different from the pure mathematic type of fields and statistics in general. It's this beautiful gestaltism. And for different optimizers, see torch.optim. But we've covered a few of these things before. And finally, I'm going to put up here, and then for some common choices of loss functions and optimizers. Now, don't worry too much. This is why I'm linking all of these extra resources. A lot of this is covered in the book. So as we just said, set up loss function optimizer. We just talked about these things, but I mean, you can just go to this book website and reference it. Oh, we don't want that. We want this link. Come on, Daniel, you can't even copy and paste. How are you supposed to code? I know I've been promising code this whole time, so let's write some. So let's set up the loss function. What did we say it was? We're going to call it LOSSFN for loss function. And we're going to call BCE with logits loss. So BCE with logits loss, this has the sigmoid activation function built in. Now, we haven't covered what the sigmoid activation function is, but we are going to. Don't you worry about that. Built in. In fact, if you wanted to learn what the sigmoid activation function is, how could you find out? Sigmoid activation function. But we're going to see it in action. Activation functions and neural networks. This is the beautiful thing about machine learning. There's so much stuff out there. People have written some great articles. You've got formulas here. PyTorch has implemented that behind the scenes for us. So thank you, PyTorch. But if you recall, sigmoid activation function built in, where did we discuss the architecture of a classification network? What do we have here? Right back in the 0th chapter of this little online book thing that we got here. Binary classification. We have output activation. Ooh, look at that. So sigmoid, torch.sigmoid in PyTorch. All right, and then for multi-class classification, we need the softmax. Okay, names on a page again, but this is just a reference table so we can keep coming back to. And so let's just keep going with this. I just want to highlight the fact that nn.bce loss also exists. So this requires BCE loss equals requires inputs to have gone through the sigmoid activation function prior to input to BCE loss. And so let's look up the documentation. I'm going to comment that out because we're going to stick with using this one. Now, why would we stick with using this one? Let's check out the documentation, hey? Torch.nn, and I realize this video is all over the place, but we're going to step back through BCE loss with logits. Did I even say this right? With logits loss. So with, I got the with around the wrong way. So let's check this out. So this loss combines a sigmoid layer with the BCE loss in one single class. So if we go back to the code, BCE loss is this. So if we combined nn.sequential, and then we passed in nn.sigmoid, and then we went nn.bce loss, we'd get something similar to this. But if we keep reading in the documentation, because that's just, I just literally read that it combines sigmoid with BCE loss. But if we go back to the documentation, why do we want to use it? So this version is more numerically stable than using a plain sigmoid by a BCE loss, followed by a BCE loss. As by combining the operations into one layer, we take advantage of the log sum X trick for numerical stability. Beautiful. So if we use this log function, loss function, for our binary cross entropy, we get some numeric stability. Wonderful. So there's our loss function. We've got the sigmoid activation function built in. And so we're going to see the difference between them later on, like in the flesh. Optimizer, we're going to choose, let's stick with SGD, hey? Old faithful, stochastic gradient descent, and we have to set the parameters here, the params, equal to our model parameters. We'd be like, hey, stochastic gradient descent, please update, if we get another code cell behind here, please update our model parameters, with respect to the loss, because we'd like our loss function to go down. So these two are going to work in tandem again when we write our training loop, and we'll set our learning rate to 0.1. We'll see where that gets us. So that's what the optimizer is going to do. It's going to optimize all of these parameters for us, which is amazing. And the principle would be the same, even if there was 100 layers here and 10,000, a million different parameters here. So we've got a loss function, we've got an optimizer, and how about we create an evaluation metric? So let's calculate accuracy at the same time, because that's very helpful with classification problems, is accuracy. Now, what is accuracy? Well, we could look up formula for accuracy. So true positive over true positive plus true negative times 100. Okay, let's see if we can implement something similar to that just using pure PyTorch. Now, why would we want accuracy? Because the accuracy is out of 100 examples, what percentage does our model get right? So for example, if we had a coin toss and we did 100 coin tosses and our model predicted heads 99 out of 100 times and it was right every single time, it might have an accuracy of 99% because it got one wrong. So 99 out of 100, it gets it right. So def accuracy fn, accuracy function. We're going to pass it y true. So remember, any type of evaluation function or loss function is comparing the predictions to the ground truth labels. So correct equals, this is going to see how many of our y true or y preds are correct. So torch equal stands for, hey, how many of these samples, y true, are equal to y pred? And then we're going to get the sum of that, and we need to get the item from that because we want it as a single value in Python. And then we're going to calculate the accuracy, ACC stands for accuracy, equals correct divided by the length of samples that we have as input, and then we're going to times that by 100 and then return the accuracy. Wonderful. So we now have an accuracy function. We're going to see how all of three of these come into play when we write a training loop, which we might as well get started on the next few videos, hey? I'll see you there. Welcome back. In the last video, we discussed some different loss function options for our classification models. So we learned that if we're working with binary cross entropy or binary classification problems, we want to use binary cross entropy. And PyTorch has two different types of binary cross entropy, except one is a bit more numerically stable. That's the BCE with Logit's loss because it has a sigmoid activation function built in. So that's straight from the PyTorch documentation. And that for optimizer-wise, we have a few different choices as well. So if we check out this section here of the PyTorch book, we have a few different loss functions and optimizers for different problems and the PyTorch code that we can implement. But the premise is still the same across the board of different problems. The loss function measures how wrong our model is. And the goal of the optimizer is to optimize the model parameters in such a way that the loss function goes down. And we also implemented our own accuracy function metric, which is going to evaluate our model's predictions using accuracy as an evaluation metric rather than just loss. So let's now work on training a model. So what should we do first? Well, do you remember the steps in a PyTorch training loop? So to train our model, we're going to need to build a training loop. So if you watched the video on the PyTorch, so if you can Google unofficial PyTorch song, you should find my, there we go, the unofficial PyTorch optimization loop song. We're not going to watch that. That's going to be a little tidbit for the steps that we're going to code out, but that's just a fun little jingle to remember these steps here. So if we go into the book section, this is number 3, train model, exactly where we're up to here. But we have PyTorch training loop steps. Remember, for an epoch in a range, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. We keep singing this all day. You could keep reading those steps all day, but it's better to code them. But let's write this out. So forward pass, 2, calculate the loss, 3, optimize a zero grad, 4, what do? Loss backward, so back propagation. I'll just write that up in here, back propagation. We've linked to some extra resources if you'd like to find out what's going on in back propagation. We're focused on code here, and then gradient descent. So, or optimize a step. So build a training loop with the following steps. However, I've kind of mentioned a few things that need to be taken care of before we talk about the forward pass. So we've talked about logits. We looked up what the hell is a logit. So if we go into this Stack Overflow answer, we saw machine learning. What is a logit? How about we see that? We need to do a few steps. So I'm going to write this down. Let's get a bit of clarity about us, Daniel. We're kind of all over the place at the moment, but that's all right. That's the exciting part of machine learning. So let's go from raw logits to prediction probabilities to prediction labels. That's what we want, because to truly evaluate our model, we want to, so let's write in here, our model outputs are going to be raw logit. So that's the definition of a logit in machine learning and deep learning. You might read some few other definitions, but for us, the raw outputs of our model 0, are going to be referred to as logits. So then model 0, so whatever comes out of here are logits. So we can convert these logits into prediction probabilities by passing them to some kind of activation function, e.g. sigmoid for binary cross-entropy, and softmax for multi-class classification. I've got binary classification. I have to sound it out every time I spell it. For binary classification. So classification. So we're going to see multi-class classification later on, but we want some prediction probabilities. We're going to see what they look like in a minute. So we want to go from logits to prediction probabilities to prediction labels. Then we can convert our model's prediction probabilities to prediction labels by either rounding them or taking the argmax. So round is for binary classification, and argmax will be for the outputs of the softmax activation function. But let's see it in action first. So I've called the logits are the raw outputs of our model with no activation function. So view the first 5 outputs of the forward pass on the test data. So of course our model is still instantiated with random values. So we're going to set up a variable here, y_logits, and model 0, we're going to pass it the test data. So xtest, not text, to device, because our model is currently on our CUDA device and we need our test data on the same device or target device. Remember, that's why we're writing device agnostic code, so this would work regardless of whether there's a GPU active or not. Let's have a look at the logits. Oh, okay. Right now, we've got some positive values here, and we can see that they're on the CUDA device, and we can see that they're tracking gradients. Now, ideally, we would have run torch.inference mode here, because we're making predictions, and the rule of thumb is whenever you make predictions with your model, you turn it into eval mode, We just have to remember to turn it back to train when we want to train, and you run torch.inference mode. So we get a very similar setup here, we just don't have the gradients being tracked anymore. Okay, so these are called logits. The logits are the raw outputs of our model without being passed to any activation function. So an activation function is something a little separate from a layer. So if we come up here, we've used layer. So the neural networks that we start to build and the ones that you'll subsequently build are comprised of layers and activation functions. We're going to make the concept of an activation function a little bit more clear later on, but for now, just treat it all as some form of mathematical operation. So if we were to pass data through this model, what is happening? Well, it's going through the linear layer. Now, recall, we've seen this a few times now, torch and then linear. If we pass data through a linear layer, it's applying the linear transformation on the incoming data. So it's performing this mathematical operation behind the scenes. So y, the output, equals the input, x, multiplied by a weight tensor, a, this could really be w, which is transposed, so that this is doing a dot product, plus a bias term here. And then if we jump into our model state dict, we've got weight and we've got bias. So that's the formula that's happening in these two layers. It will be different depending on the layer that we choose, but for now we're sticking with linear. And so that the raw output of our data going through our two layers, the logits, is going to be this information here. However, it's not in the same format as our test data. And so if we want to make a comparison to how good our model is performing, we need apples to apples. So we need this in the same format as this, which it's not, of course. So we need to go to a next step. Let's use the sigmoid. So use the sigmoid activation function on our model logits. So why are we using sigmoid? Well, recall, in a binary classification architecture, the output activation is the sigmoid function here. So now let's jump back into here, and we're going to create some pred probs. And what this stands for on our model logits, to turn them into prediction probabilities. So y pred probs equals torch sigmoid y logits. And now let's have a look at y pred probs. What do we get from this? Oh, well, we still get numbers on a page. Goodness gracious me. But the important point now is that they've gone through the sigmoid activation function, which is now we can pass these to a torch.round function. Let's have a look at this. Torch.round, and what do we get? Pred probs. Oh, the same format as what we've got here. Now you might be asking, like, why don't we just put torch.round here? Well, that's a little, this step is required to, we can't just do it on the raw logits. We need to use the sigmoid activation function here to turn it into prediction probabilities. And now what is a prediction probability? Well, that's a value usually between 0 and 1 for how likely our model thinks it's a certain class. And in the case of binary cross entropy, these prediction probability values, let me just write this out in text. So for our prediction probability values, we need to perform a range style rounding on them. So this is a decision boundary. So this will make more sense when we go y pred probs. If it's equal to 0.5 or greater than 0.5, we set y equal to 1. So y equal 1. So class 1, whatever that is, a red dot or a blue dot, and then y pred probs. If it is less than 0.5, we set y equal to 0. So this is class 0. You can also adjust this decision boundary. So say if you wanted to increase this value, so anything over 0.7 is 1 and below that is 0. But generally, most commonly, you'll find it split at 0.5. So let's keep going. Let's actually see this in action. So how about we recode this? So find the predicted probabilities in So we want the predicted labels. That's what we want. So when we're evaluating our model, we want to convert the outputs of our model. The outputs of our model are here, the logits. The raw outputs of our model are logits. And then we can convert those logits to prediction probabilities using the sigmoid function on the logits. And then we want to find the predicted labels. So we go raw logits, output of our model, prediction probabilities after passing them through an activation function, and then prediction labels. This is the steps we want to take with the outputs of our model. So find the predicted labels. Let's go in here. A little bit different to our regression problem previously, but nothing we can't handle. Torch round, we're going to go ypred probs. So I like to name it ypred probs for prediction probabilities and ypreds for prediction labels. Now let's go in full if we wanted to. So ypred labels equals torch.round, torch.sigmoid, so sigmoid activation function for binary cross entropy, and model 0 xtest.toDevice. Truly this should be within inference mode code, but for now we'll just leave it like this to have a single example of what's going on here. Now I just need to count 1, 2, that's where we want the index. We just want it on 5 examples. So check for equality, and we want print torch equal, we're going to check ypreds.squeeze is equal to ypred labels. So it's just, we're doing the exact same thing, and we need squeeze here to get rid of the extra dimension that comes out. You can try doing this without squeeze. So get rid of extra dimension once again. We want ypreds.squeeze. Fair bit of code there, but this is what's happened here. We create ypreds. So we turn the ypred probs into ypreds. And then we just do the full step over again. So we make predictions with our model. We get the raw logits. So this is logits to pred probs to pred labels. So the raw outputs of our model are logits. We turn the logits into prediction probabilities using torch sigmoid, and we turn the prediction probabilities into prediction labels using torch.round, and we fulfill this criteria here. So everything above 0.5, this is what torch.round does, turns it into a 1. Everything below 0.5 turns it into a 0. The predictions right now are going to be quite terrible because our model is using random numbers, but ypreds found with the steps above is the same as ypred labels, doing them all in one hit, thanks to this check for equality using torch equal, ypreds.squeeze, and we just do the squeeze to get rid of the extra dimensions, and we have out here some labels that look like our actual ytest labels. They're in the same format, but of course they're not the same values because this model is using random weights to make predictions. So we've done a fair few steps here, but I believe we are now in the right space to start building a training and test loop. So let's write that down here, 3.2, building a training and testing loop. You might want to have a go at this yourself. So we've got all the steps that we need to do the forward pass, but the reason we've done this step here, the logits, then the pred probs and the pred labels, is because the inputs to our loss function up here, this requires, so BCE with logits loss requires what? Well, we're going to see that in the next video, but I'd encourage you to give it a go at implementing these steps here. Remember the jingle? For an epoch in a range, do the forward pass, calculate the loss, which is BCE with logits loss, optimize a 0 grad, which is this one here, loss backward, optimize a step, step, step. Let's do that together in the next video. Welcome back. In the last few videos, we've been working through creating a model for a classification problem. And now we're up to training a model. And we've got some steps here, but we started off by discussing the concept of logits. Logits are the raw output of the model, whatever comes out of the forward functions of the layers in our model. And then we discussed how we can turn those logits into prediction probabilities using an activation function, such as sigmoid for binary classification, and softmax for multi-class classification. We haven't seen softmax yet, but we're going to stick with sigmoid for now because we have binary classification data. And then we can convert that from prediction probabilities to prediction labels. Because remember, when we want to evaluate our model, we want to compare apples to apples. We want our model's predictions to be in the same format as our test labels. And so I took a little break after the previous video. So my Colab notebook has once again disconnected. So I'm just going to run all of the cells before here. It's going to reconnect up here. We should still have a GPU present. That's a good thing about Google Colab, is that if you change the runtime type to GPU, it'll save that wherever it saves the Google Colab notebook, so that when you restart it, it should still have a GPU present. And how can we check that, of course? Well, we can type in device, we can run that cell, and we can also check NVIDIA SMI. It'll tell us if we have an NVIDIA GPU with CUDA enabled ready to go. So what's our device? CUDA, wonderful. And NVIDIA SMI, excellent. I have a Tesla P100 GPU ready to go. So with that being said, let's start to write a training loop. Now we've done this before and we've got the steps up here. Do the forward pass, calculate the loss. We've spent enough on this, so we're just going to start jumping into write code. There is a little tidbit in this one though, but we'll conquer that when we get to it. So I'm going to set a manual seed, torch.manual seed, and I'm going to use my favorite number 42. This is just to ensure reproducibility if possible. Now, I also want you to be aware of, there is also another form of random seed, manual seed, which is a CUDA random seed. Do we have the PyTorch? Yeah, reproducibility. So torch.cuda.manualseed.seed. There is a CUDA seed somewhere. Let's try and find out. CUDA. I think PyTorch have just had an upgrade to their documentation. Seed. Yeah, there we go. Okay. I knew it was there. So torch.cuda.manual seed. So if we're using CUDA, we have a CUDA manual seed as well. So let's see what happens if we put that, torch.cuda.manual seed 42. We don't necessarily have to put these. It's just to try and get as reproducible as numbers as possible on your screen and my screen. Again, what is more important is not necessarily the numbers exactly being the same lining up between our screens. It's more so the direction of which way they're going. So let's set the number of epochs. We're going to train for 100 epochs. Epochs equals 100. But again, as you might have guessed, the CUDA manual seed is for if you're doing operations on a CUDA device, which in our case we are, well, then perhaps we'd want them to be as reproducible as possible. So speaking of CUDA devices, let's put the data to the target device because we're working with, or we're writing data agnostic code here. So I'm going to write xtrain ytrain equals xtrain2 device, comma, ytrain.to device. That'll take care of the training data. And I'm going to do the same for the testing data equals xtest2 device. Because if we're going to run our model on the CUDA device, we want our data to be there too. And the way we're writing our code is going to be device agnostic. Have I said that enough yet? So let's also build our training and evaluation loop. Because we've covered the steps in here before, we're going to start working a little bit faster through here. And don't worry, I think you're up to it. So for an epoch in a range of epochs, what do? We start with training. So let me just write this. Training. Model 0.train, that's the model we're working with. We call the train, which is the default, but we're going to do that anyway. And as you might have guessed, the code that we're writing here is, you can functionize this. So we're going to do this later on, but just for now, the next couple of videos, the next module or two, we're going to keep writing out the training loop in full. So this is the part, the forward pass, where there's a little bit of a tidbit here compared to what we've done previously. And that is because we're outputting raw logits here if we just pass our data straight to the model. So model 0 xtrain, and we're going to squeeze them here to get rid of an extra dimension. You can try to see what the output sizes look like without squeeze, but I'm just going to call squeeze here. Remember, squeeze removes an extra one dimension from a tensor. And then to convert it into prediction labels, we go torch.round and torch.sigmoid, because torch.sigmoid is an activation function which is going to convert logits into what? Convert the logits into prediction probabilities. So y logits, and I'm just going to put a note here. So this is going to go turn logits into pred probs into pred labels. So we've done the forward pass. So that's a little tidbit there. We could have done all of this in one step, but I'll show you why we broke this apart. So now we're going to calculate loss/accuracy. We don't necessarily have to calculate the accuracy, but we did make an accuracy function up here so that we can calculate the accuracy during training. We could just stick with only calculating the loss, but sometimes it's cool to visualize different metrics, loss plus a few others while your model is training. So let's write some code to do that here. So we'll start off by going loss equals loss fn and y logits. Here's the difference of what we've done before. Previously in the notebook 01, we're up to 02 now, we passed in the prediction right here. But because, what's our loss function? Let's have a look at our loss function. Let's just call that, see what it returns. BCE with logits loss. So the BCE with logits expects logits as input. So as you might have guessed, loss function without logits, if we had nn.bce loss, notice how we haven't got with logits, and then we called loss fn, fn stands for function by the way, without logits, what do we get? So BCE loss, so this loss expects prediction probabilities as input. So let's write some code to differentiate between these two. As I said, we're going to be sticking with this one. Why is that? Because if we look up torch BCE with logits loss, the documentation states that it's more numerically stable. So this loss combines a sigmoid layer and the BCE loss into one single class and is more numerically stable. So let's come back here. We'll keep writing some code. And the accuracy is going to be accuracy fn. So our accuracy function, there's a little bit of a difference here, is y true equals y trained for the training data. So this will be the training accuracy. And then we have y pred equals y pred. So this is our own custom accuracy function that we wrote ourselves. This is a testament to the Pythonic nature of PyTorch as well. We've just got a pure Python function that we've slotted into our training loop, which is essentially what the loss function is behind the scenes. Now, let's write here, nn.bce with logits loss expects raw logits, so the raw output of our model, as input. Now, what if we were using a BCE loss on its own here? Well, let's just write some code for that. So let's call loss function, and then we want to pass in y pred, or we can just go y, or torch sigmoid. So why would we pass in torch sigmoid on the logits here? Because remember, calling torch.sigmoid on our logits turns our logits into prediction probabilities. And then we would pass in y train here. So if this was BCE loss, this expects prediction probabilities as input. So does that make sense? That's the difference between with logits. So our loss function requires logits as input, whereas if we just did straight up BCE loss, we need to call torch.sigmoid on the logits because it expects prediction probabilities as input. Now, I'm going to comment that out because our loss function is BCE with logits loss. But just keep that in mind. If for some reason you stumble across some PyTorch code that's using BCE loss, not BCE with logits loss, and you find that torch.sigmoid is calling here, or you come across some errors because your inputs to your loss function are not what it expects. So with that being said, we can keep going with our other steps. So we're up to optimizer 0 grad. So optimizer.0grad. Oh, this is step 3, by the way. And what's after this? Once we've 0 gradded the optimizer, we do number 4, which is loss backward. We can go loss backward. And then we go, what's next? Optimizer step, step, step. So optimizer.step. And I'm singing the unofficial PyTorch optimization loop song there. This is backpropagation. Calculate the gradients with respect to all of the parameters in the model. And the optimizer step is update the parameters to reduce the gradients. So gradient descent, hence the descent. Now, if we want to do testing, well, we know what to do here now. We go model 0, what do? We call model.eval when we're testing. And if we're making predictions, that's what we do when we test. We make predictions on the test data set using the patterns that our model has learned on the training data set. We turn on inference mode because we're doing inference. We want to do the forward pass. And of course, we're going to compute the test logits because logits are the raw output of our model with no modifications. xtest.squeeze. We're going to get rid of an extra 1 dimension there. Then we create the test pred, which is, we have to do a similar calculation to what we've done here for the test pred, which is torch.round. For our binary classification, we want prediction probabilities, which we're going to create by calling the sigmoid function on the test logits. Prediction probabilities that are 0.5 or above to go to 1, and prediction probabilities under 0.5 to go to label 0. So 2 is calculate the test loss / accuracy. How would we do this? Well, just as we've done before. And we're going to go loss fn test logits, because our loss function we're using what? We're using BCE with logits loss, expects logits as input. Where do we find that out? In the documentation, of course. Then we come back here. Test logits, we're going to compare that to the y test labels. And then for the test accuracy, what are we going to do? We're going to call accuracy fn on y true equals y test and y pred equals test pred. Now you might be thinking, why did I switch up the order here for these? Oh, and by the way, this is important to know with logits loss. So with these loss functions, the order here matters of which way you put in your parameters. So predictions come first and then true labels for our loss function. You might be wondering why I've done it the reverse for our accuracy function, y true and y pred. That's just because I like to be confusing. Well, not really. It's because if we go to scikit-learn, I base a lot of my structured code off how scikit-learn structures things. The scikit-learn metrics accuracy score goes y true, y pred. So I based it off that order because the scikit-learn metrics package is very helpful. So I've based our metric, evaluation metric function, off this one. Whereas PyTorch's loss function does it in the reverse order, and it's important to get these in the right order. Exactly why they do it in that order, I couldn't tell you why. And we've got one final step, which is to print out what's happening. Happening. So how about we go, we're doing a lot of epochs here, 100 epochs. So we'll divide the epoch by 10 to print out every epoch, or every 10th epoch, sorry. And we have a couple of different metrics that we can print out this time. So we're going to print out the epoch number, epoch, and then we're going to print out the loss. So loss, how many decimal points? We'll go 0.5 here. This is going to be the training loss. We'll also do the accuracy, which will be the training accuracy. We could write train acc here for our variable to be a little bit, make them a little bit more understandable. And then we go here, but we're just going to leave it as loss and accuracy for now because we've got test loss over here. Test loss. And we're going to do the same, 5 decimal points here. And then we're going to go test accuracy as well. Test acc dot. We'll go 2 for the accuracy. And because it's accuracy, we want a percentage. So this is the percent out of 100 guesses. What's the percentage that our model gets right on the training data and the testing data, as long as we've coded all the functions correctly. Now, we've got a fair few steps here. My challenge to you is to run this, and if there are any errors, try to fix them. No doubt there's probably 1 or 2 or maybe more that we're going to have to fix in the next video. But speaking of next videos, I'll see you there. Let's train our first classification model. Oh, this is very exciting. I'll see you soon. Welcome back. In the last video, we wrote a mammoth amount of code, but nothing that we can't handle. We've been through a lot of these steps. We did have to talk about a few tidbits between using different loss functions, namely the BCE loss, which is binary cross entropy loss, and the BCE with logits loss. We discussed that the BCE loss in PyTorch expects prediction probabilities as input, so we have to convert our model's logits. Logits are the raw output of the model to prediction probabilities using the torch.sigmoid activation function. And if we're using BCE with logits loss, it expects raw logits as input, as sort of the name hints at. And so we just pass it straight away, the raw logits. Whereas our own custom accuracy function compares labels to labels. And that's kind of what we've been stepping through over the last few videos, is going from logits to pred probs to pred labels, because that's the ideal output of our model, is some kind of label that we as humans can interpret. And so let's keep pushing forward. You may have already tried to run this training loop. I don't know if it works. We wrote all this code together in the last video, and there's probably an error somewhere. So you ready? We're going to train our first classification model together for 100 epochs. If it all goes to plan, in 3, 2, 1, let's run. Oh my gosh, it actually worked the first go. I promise you I didn't change anything in here from the last video. So let's inspect what's going on. It trains pretty fast. Why? Well, because we're using a GPU, so it's going to be accelerated as much as it can anyway. And our data set is quite small and our network is quite small. So you won't always get networks training this fast. It did 100 epochs in like a second. So the loss, 0.69973. It doesn't go down very much. The accuracy even starts high and then goes down. What's going on here? Our model doesn't seem to be learning anything. So what would an ideal accuracy be? An ideal accuracy is 100, and what's an ideal loss value? Well, 0, because lower is better for loss. This is confusing. And now if we go have a look at our blue and red dots, where's our data? So I reckon, do we still have a data frame here? How many samples do we have of each? Let's inspect. Let's do some data analysis. Where do we create a data frame? Here. Now, circles. Do we still have this instantiated? Circles.label. We're going to call on pandas here. Value counts. Is this going to output how many of each? Okay. Wow. We've got 500 of class 1 and 500 of class 0. So we have 500 red dots and blue dots, which means we have a balanced data set. So if we're basically trying to predict heads or tails here. So if we're getting an accuracy of under 50% or about 50% if you rounded it up, our model is basically doing as well as guessing. Well, what gives? Well, I think we should get visual with this. So let's make some predictions with our model, because these are just numbers on the page. It's hard to interpret what's going on, but our intuition now is because we have 500 samples of each, or in the case of the training data set, we have 400 of each because we have 800 samples in the training data set, and we have in the testing data set, we have 200 total samples, so we have 100 of each. We're basically doing a coin flip here. Our model is as good as guessing. So, time to investigate why our model is not learning. And one of the ways we can do that is by visualizing our predictions. So let's write down here from the metrics, it looks like our model isn't learning anything. So to inspect it, let's make some predictions and make them visual. And we'll write down here, in other words, visualize, visualize, visualize. All right. So we've trained a model. We've at least got the structure for the training code here. Like, this is the right training code. We've written this code before. So you know that this setup for training code does allow a model to train. So there must be something wrong with either how we've built our model, the data set, but let's keep going and investigate together. So to do so, I've got a function that I've pre-built earlier. Did I mention that we're learning side by side of a machine learning cooking show? So this is an ingredient I prepared earlier, a part of a dish. So to do so, we're going to import a function called plot decision, or maybe I'll turn this into code. Plot decision boundary. Welcome to the cooking show. Cooking with machine learning. What model will we cook up today? So if we go to PyTorch Deep Learning, well, it's already over here, but this is the home repo for the course. The link for this will be scattered everywhere. But there's a little function here called helperfunctions.py, which I'm going to fill up with helper functions throughout the course. And this is the one I'm talking about here. Plot decision boundary. Now we could just copy this into our notebook, or I'm going to write some code to import this programmatically so we can use other functions from in here. Here's our plot predictions function that we made in the last section, 0, 1. But this plot decision boundary is a function that I got inspired by to create from madewithml.com. Now, this is another resource, a little bit of an aside. I highly recommend going through this by Goku Mohandas. It gives you the foundations of neural networks and also ML ops, which is a field which is based on getting your neural networks and machine learning models into applications that other people can use. So I can't recommend this resource enough. So please, please, please check that out if you want another resource for machine learning. But this is where this helper function came from. So thank you, Goku Mohandas. I've made a little bit of modifications for this course, but not too many. So we could either copy that, paste it in here, or we could write some code to import it for us magically, or using the power of the internet, right? Because that's what we are. We're programmers, we're machine learning engineers, we're data scientists. So from pathlib, so the request module in Python is a module that allows you to make requests. A request is like going to a website, hey, I'd like to get this code from you or this information from you. Can you please send it to me? So that's what that allows us to do. And pathlib, we've seen pathlib before, but it allows us to create file paths. Because why? Well, we want to save this helperfunction.py script to our Google Colab files. And so we can do this with a little bit of code. So download helper functions from Learn PyTorch repo. If it's not already downloaded. So let's see how we can do that. So we're going to write some if-else code to check to see if the path of helper functions.py already exists. We don't want to download it again. So at the moment it doesn't exist. So this if statement is going to return false. So let's just print out what it does if it returns true. Helper functions.py already exists. We could even probably do a try and except loop here, but if else will help us out for now. So if it exists, else, print, downloading helper functions.py. So ours doesn't exist, so it's going to make a request, or let's set up our requests. Requests.get, and here's where we can put in a URL, but we need the raw version of it. So this is the raw version. If we go back, this is just PyTorch Deep Learning, the repo for this course, /helper functions. If I click raw, I'm going to copy that. Oh, don't want to go in there. I want to go into request get, type that in. This has to be in a string format. So we get the raw URL, and then we're going to go with open. We're going to open a file called helperfunctions.py, and we're going to set the context to be write binary, which is WB, as file. F is a common short version of writing file, because we're going to call file.write and then request.content. So this code is basically saying, hey, requests, get the information that's at this link here, which is, of course, all of this code here, which is a Python script. And then we're going to create a file called helperfunctions.py, which gives us write permissions. We're going to name it F, which is short for file. And then we're going to call on it file.write the content of the request. So instead of talking through it, how about we see it in action? We'll know if it works if we can, from helper functions, import plot predictions. We're going to use plot predictions later on, as well as plot decision boundary. So plot predictions we wrote in the last section. Wonderful. I'm going to write here, downloading helperfunctions.py. Did it work? We have helper functions.py. Look at that. We've done it programmatically. Can we view this in Google Colab? Oh my goodness, yes we can. Look at that. So this may evolve by the time you do the course, but these are just some general helper functions rather than writing all of this out. If you would like to know what's going on in plot decision boundary, I encourage you to read through here and what's going on. You can step by step it yourself. There is nothing here that you can't tackle yourself. It's all just Python code. No secrets, just Python code. We're making predictions with a PyTorch model, and then we're testing for multi-class or binary. So we're going to get out of that. But now let's see, the ultimate test is if the plot decision boundary function works. So again, we could discuss plot decision boundary of the model. We could discuss what it does behind the scenes till the cows come home. But we're going to see it in real life here. I like to get visual. So fig size 12.6. We're going to create a plot here because we are adhering to the Data Explorer's motto of visualize, visualize, visualize. And we want a subplot because we're going to compare our training and test sets here. Train, and then we're going to go PLT, or actually, we'll plot the first one. Plot decision boundary. Now, because we're doing a training plot here, we're going to pass in model 0 and xtrain and ytrain. Now, this is the order that the parameters go in. If we press Command-Shift-Space, I believe Google Colab, if it's working with me, will put up a doc string. There we go, plot decision boundary. Look at the inputs that it takes. Model, which is torch_nn.module. And we've got x, which is our x value, which is a torch tensor, and y, which is our torch tensor value here. So that's for the training data. Now, let's do the same for the testing data. Plot.subplot. This is going to be 1, 2, 2 for the index. This is just number of rows of the plot, number of columns, and this is the index. So this plot will appear on the first slot. We're going to see this anyway. Anything below this code will appear on the second slot. plt.title, and we're going to call this one test. And then we're going to call plot decision boundary. If this works, this is going to be some serious magic. I love visualization functions in machine learning. Okay, you ready? 3, 2, 1, let's check it out. How's our model doing? Oh, look at that! Oh, now it's clear. So behind the scenes, this is the plots that plot decision boundary is making. Of course, this is the training data. This is the testing data. Not as many dot points here, but the same sort of line of what's going on. So this is the line that our model is trying to draw through the data. No wonder it's getting about 50% accuracy and the loss isn't going down. It's just trying to split the data straight through the middle. It's drawing a straight line, but our data is circular. Why do you think it's drawing a straight line? Well, do you think it has anything to do with the fact that our model is just made using pure linear layers? Let's go back to our model. What's it comprised of? Just a couple of linear layers. What's a linear line? If we look up linear line, is this going to work with me? I don't actually think. It might. There we go. Linear line. All straight lines. So I want you to have a think about this. Even if you're completely new to deep learning, you can answer this question, can we ever separate this circular data with straight lines? I mean, maybe we could if we drew straight lines here, but then trying to curve them around. But there's an easier way. We're going to see that later on. For now, how about we try to improve our model? So the model that we built, we've got 100 epochs. I wonder if our model will improve if we trained it for longer. So that's a little bit of a challenge before the next video. See if you can train the model for 1,000 epochs. Does that improve the results here? And if it doesn't improve the results here, have a think about why that might be. I'll see you in the next video. Welcome back. In the last video, we wrote some code to download a series of helper functions from our helperfunctions.py. And later on, you'll see why this is quite standard practice as you write more and more code, is to write some code, store them somewhere, such as a Python script like this. And then instead of us rewriting everything that we have in helper functions, we just import them and then use them later on. This is similar to what we've been doing with PyTorch. PyTorch is essentially just a collection of Python scripts that we're using to build neural networks. Well, there's a lot more than what we've just done. I mean, we've got one here, but PyTorch is a collection of probably hundreds of different Python scripts. But that's beside the point. We're trying to train a model here to separate blue and red dots. But our current model is only drawing straight lines. And I got you to have a think about whether our straight line model, our linear model, could ever separate this data. Maybe it could. And I issued the challenge to see if it could if you trained for 1,000 epochs. So, did it improve at anything? Is the accuracy any higher? Well, speaking of training for more epochs, we're up to section number 5, improving a model. This is from a model perspective. So now let's discuss some ways if you were getting results after you train a machine learning model or a deep learning model, whatever kind of model you're working with, and you weren't happy with those results. So how could you go about improving them? So this is going to be a little bit of an overview of what we're going to get into. So one way is to add more layers. So give the model more chances to learn about patterns in the data. Why would that help? Because if our model currently has 2 layers, model 0.stateDict, well, we've got however many numbers here, 20 or so. So this is 0th layer, this is the first layer. If we had 10 of these, well, we'd have 10 times the amount of parameters to try and learn the patterns in this data, a representation of this data. Another way is to add more hidden units. So what I mean by that is we created this model here, and each of these layers has 5 hidden units. The first one outputs, out features equals 5, and this one takes in features equals 5. So we could go from 5 hidden units to 10 hidden units. The same principle as above applies here, is that the more parameters our model has to represent our data, the potentially, now I say potentially here because some of these things might not necessarily work. So our data set is quite simple. So maybe if we added too many layers, our model's trying to learn things that are too complex. It's trying to adjust too many numbers for the data set that we have. The same thing for more hidden units. What other options do we have? Well, we could fit for longer, give the model more of a chance to learn because every epoch is one pass through the data. So maybe 100 times looking at this data set wasn't enough. So maybe you could fit for 1,000 times, which was the challenge. Then there's changing the activation functions, which we're using sigmoid at the moment, which is generally the activation function you use for a binary classification problem. But there are also activation functions you can put within your model. There's a little hint. We'll get to that later. Then there's change the learning rate. So the learning rate is the amount the optimizer will adjust these every epoch. And if it's too small, our model might not learn anything because it's taking forever to change these numbers. But if also on the other side of things, if the learning rate is too high, these updates might be too large and our model might just explode. There's an actual problem in machine learning called exploding gradient problem, where the numbers just get too large. On the other side, there's also a vanishing gradients problem, where the gradients just go basically to 0 too quickly. And then there's also change the loss function, but I feel like for now, sigmoid and binary cross entropy are pretty good, pretty standard. So we're going to have a look at some options here, add more layers and fit for longer, maybe changing the learning rate, but let's just add a little bit of color to what we've been talking about. Right now, we've fit the model to the data and made a prediction. I'm just going to step through this. Where are we up to? We've done this, we've done this, we've done these two, we've built a training loop, we've fit the model to the data, made a prediction, we've evaluated our model visually, and we're not happy with that. So we're up to number 5. We're going to improve through experimentation. We don't need to use TensorBoard just yet. We're going to talk about this as a high level. TensorBoard is a tool or a utility from PyTorch, which helps you to monitor experiments. We'll see that later on. And then we'll get to this. We won't save our model until we've got one that we're happy with. And so, if we look at what we've just talked about, improving a model from a model's perspective, let's talk about the things we've talked about with some color this time. So, say we've got a model here. This isn't the exact model that we're working with, but it's similar structure. We've got 1, 2, 3, 4 layers. We've got a loss function, BCE with logits loss. We've got an optimizer, stochastic gradient descent, and if we did write some training code, this is 10 epochs. And then the testing code here, I've just cut it out because it wouldn't fit on the slide. Then if we wanted to go to a larger model, let's add some color here so we can highlight what's happening. Adding layers. Okay, so this one's got 1, 2, 3, 4, 5, 6 layers. And we've got another color here, which is, I'd say this is like a little bit of a greeny blue. Increase the number of hidden units. Okay, so the hidden units are these features here. We've gone from 100 to 128 to 128. Remember, the out features of a previous layer have to line up with the in features of a next layer. And then we've gone to 256. Wow! So remember how I said multiples of 8 are pretty good generally in deep learning? Well, this is where these numbers come from. And then what else do we have? Change/add activation functions. We haven't seen this before, nn.relu. If you want to jump ahead and have a look at what nn.relu is, how would you find out about it? Well, I'd just Google nn.relu, but we're going to have a look at what this is later on. We can see here that this one's got 1, but this larger model has some relus scattered between the linear layers. Maybe that's a hint. If we combine a linear layer with a relu, what's a relu layer? I'm not going to spoil this, we're going to find out later on. Change the optimization function. Oh, okay, so we've got SGD. Do you recall how I said Atom is another popular one that works fairly well across a lot of problems as well? So Atom might be a better option for us here. The learning rate as well. So maybe this learning rate was a little too high, and so we've divided it by 10. And then finally, fitting for longer. So instead of 10 epochs, we've gone to 100. So how about we try to implement some of these with our own model to see if it improves what we've got going on here. Because frankly, this isn't satisfactory. We're trying to build a neural network here. Neural networks are supposed to be these models that can learn almost anything, and we can't even separate some blue dots from some red dots. So in the next video, how about we run through writing some code to do some of these steps here? In fact, if you want to try yourself, I'd highly encourage that. So I'd start with trying to add some more layers and add some more hidden units and fitting for longer. You can keep all of the other settings the same for now. But I'll see you in the next video. Welcome back. In the last video, we discussed some options to improve our model from a model perspective. And namely, we're trying to improve it so that the predictions are better, so that the patterns it learns better represent the data, so we can separate blue dots from red dots. And you might be wondering why we said from a model perspective here. So let me just write these down. These options are all from a model's perspective because they deal directly with the model rather than the data. So there's another way to improve a model's results is if the model was sound already. In machine learning and deep learning, you may be aware that generally if you have more data samples, the model learns or gets better results because it has more opportunity to learn. There's a few other ways to improve a model from a data perspective, but we're going to focus on improving a model from a model's perspective. So, and because these options are all values we as machine learning engineers and data scientists can change, they are referred to as hyperparameters. So a little bit of an important distinction here. Parameters are the numbers within a model. The parameters here, like these values, the weights and biases, are parameters, are the values a model updates by itself. Hyperparameters are what we as machine learning engineers and data scientists, such as adding more layers, more hidden units, fitting for longer, number of epochs, activation functions, learning rate, loss functions, are hyperparameters because they're values that we can change. So let's change some of the hyperparameters of our model. So we'll create circle model v1. We're going to import from nn.module as well. We could write this model using nn.sequential, but we're going to subclass nn.module for practice. Why would we use nn.sequential? Well, because as you'll see, our model is not too complicated, but we subclass nn.module. In fact, nn.sequential, so if we write here, nn.sequential, is also a version of nn.module. But we subclass nn.module here for practice, and for later on if we wanted to, or if you wanted to make more complex models, you're going to see a subclass of nn.module a lot in the wild. So the first change we're going to update is the number of hidden units. So out features, I might write this down before we do it. Let's try and improve our model by adding more hidden units. So this will go from 5 and we'll increase it to 10. And we want to increase the number of layers. So we want to go from 2 to 3. We'll add an extra layer and then increase the number of epochs. So we're going to go from 100 to 1,000. Now, we're going to put on our scientist hats for a second. What would be the problem with the way we're running this experiment? If we're doing all three things in one hit, why might that be problematic? Well, because we might not know which one offered the improvement, if there is any improvement, or degradation. So, just to keep in mind going forward, I'm just doing this as an example of how we can change all of these. But generally, when you're doing machine learning experiments, you'd only like to change one value at a time and track the results. So that's called experiment tracking in machine learning. We're going to have a look at experiment tracking a little later on in the course, but just keep that in mind. A scientist likes to change one variable of what's going on so that they can control what's happening. But we're going to create this next layer here, layer 2, and of course it takes the same number of out features as in features as the previous layer. This is 2 because why? Our X train has, let's look at just the first 5 samples, has 2 features. So now we're going to create self layer 3, which equals nn.linear. The in features here is going to be 10. Why? Because the layer above has out features equals 10. So what we've changed here so far is we've got hidden units previously in V0 of this model was 5. And now we've got a third layer, which previously before was 2. So these are 2 of our main changes here. And out features equals 1 because why? Let's have a look at, speaking of why, our y is just one number. So remember, the shapes, the input and output shapes of a model is one of the most important things in deep learning. We're going to see different values for these shapes later on, but because we're working with this data set, we're focused on 2 in features and 1 out feature. So now that we've got our layers prepared, what's next? Well, we have to override the forward method because every subclass of nn.module has to implement a forward method. So what are we going to do here? Well, let me just show you one option. We could go Z, which would be Z for logits. Logits is actually represented by a Z, fun fact, but you could actually put any variable here. So this could be x1, or you could reset x if you wanted to. I just look putting a different one because it's a little less confusing for me. And then we could go update Z by going self layer 2, and then because Z above is the output of layer 1, it now goes into here. And then if we go Z again equals self layer 3, what's this going to take? It's going to take Z from above. So this is saying, hey, give me X, put it through layer 1, assign it to Z, and then create a new variable Z or override Z with self layer 2 with Z from before as the input. And then we've got Z again, the output of layer 2 as the input for layer 3. And then we could return Z. So that's just passing our data through each one of these layers here. But a way that you can leverage speedups in PyTorch is to call them all at once. So layer 3, and we're going to put self dot layer 2, and this is generally how I'm going to write them, but it also, behind the scenes, because it's performing all the operations at once, you leverage whatever speedups you can get. Oh, this should be layer 1. So it goes in order here. So what's happening? Well, it's computing the inside of the brackets first. So layer 1, X is going through layer 1. And then the output of X into layer 1 is going into layer 2. And then the same again for layer 3. So this way of writing operations leverages speed ups where possible behind the scenes. And so we've done our forward method there. We're just passing our data through layers with extra hidden units and an extra layer overall. So now let's create an instance of circle model v1, which we're going to set to model 1, and we're going to write circle model v1, and we're going to send it to the target device because we like writing device agnostic code. And then we're going to check out model 1. So let's have a look at what's going on there. Beautiful. So now we have a 3-layered model with more hidden units. So I wonder if we trained this model for longer, are we going to get improvements here? So my challenge to you is we've already done these steps before. We're going to do them over the next couple of videos for completeness. But we need to what? Create a loss function. So I'll give you a hint. It's very similar to the one we've already used. And we need to create an optimizer. And then once we've done that, we need to write a training and evaluation loop for model 1. So give that a shot. Otherwise, I'll see you in the next video. We'll do this all together. Welcome back. In the last video, we subclassed nn.module to create circle model v1, which is an upgrade on circle model v0 in the fact that we added more hidden units, so from 5 to 10, and we added a whole extra layer. And we've got an instance of it ready to go. So we're up to, in the workflow, we've got our data. Well, we haven't changed the data. So we've built our new model. We now need to pick a loss function. And I hinted at before that we're going to use the same loss function as before, the same optimizer. You might have already done all of these steps. So you may know whether this model works on our data set or not. But that's what we're going to work towards finding out in this video. So we've built our new model. Now let's pick a loss function and an optimizer. We could almost do all of this with our eyes closed now. Build a training loop, fit the model to the data, make a prediction, and evaluate the model. We'll come back here, and let's set up a loss function. And by the way, if you're wondering, like, why would adding more features here, we've kind of hinted at this before, and why would an extra layer improve our model? Well, again, it's back to the fact that if we add more neurons, if we add more hidden units, and if we add more layers, it just gives our model more numbers to adjust. So look at what's going on here. Layer 1, layer 2. Look how many more we have compared to model 0.stateDict. We have all of these. This is model 0, and we just upgraded it. Look how many more we have from just adding an extra layer and more hidden units. So now we have our optimizer can change these values to hopefully create a better representation of the data we're trying to fit. So we just have more opportunity to learn patterns in our target data set. So that's the theory behind it. So let's get rid of these. Let's create a loss function. What are we going to use? Well, we're going to use nn.bce with logits loss. And our optimizer is going to be what? We're going to keep that as the same as before, torch.optim.sgd. But we have to be aware that because we're using a new model, we have to pass in params of model 1. These are the parameters we want to optimize, and the LR is going to be 0.1. Is that the same LR we used before, learning rate 0.1? Oh, potentially that, our learning rate may be too big, 0.1. Where do we create our optimizer? See, we've written a lot of code here. Optimizer, there we go, 0.1, that's all right. So we'll keep it at 0.1 just to keep as many things the same as possible. So we're going to set up torch.manualseed 42 to make training as reproducible as possible. Torch.cuda.manualseed 42. Now, as I said before, don't worry too much if your numbers aren't exactly the same as mine. The direction is more important, whether it's good or bad direction. So now let's set up epochs. We want to train for longer this time as well. So 1,000 epochs. This is one of our 3 improvements that we're trying to do. Adding more hidden units, increase the number of layers, and increase the number of epochs. So we're going to give our model 1,000 looks at the data to try and improve its patterns. So put data on the target device. We want to write device agnostic code. And yes, we've already done this, but we're going to write it out again for practice, because even though we could functionize a lot of this, it's good while we're in still the foundation stages to practice what's going on here, because I want you to be able to do this with your eyes closed before we start to functionize it. So put the training data and the testing data to the target device, whatever it is, CPU or GPU. And then we're going to, well, what's our song? For an epoch in a range. Let's loop through the epochs. We're going to start off with training. What do we do for training? Well, we set model 1 to train. And then what's our first step? Well, we have to forward pass. What's our outputs of the model? Well, the raw outputs of a model are logits. So model 1, we're going to pass it the training data. And we're going to squeeze it so that we get rid of an extra one dimension. If you don't believe me that we would like to get rid of that one dimension, try running the code without that dot squeeze. And ypred equals torch.round. And torch.sigmoid, why? We're calling sigmoid on our logits to go from logits to prediction probabilities to prediction labels. And then what do we do next? Well, we calculate the loss / accuracy to here. And remember, accuracy is optional, but loss is not optional. So we're going to pass in here, our loss function is going to take in, I wonder if it'll work with just straight up ypred. I don't think it will, because we need logits in here. Logits and train. Because why? Oh, Google Colab correcting the wrong thing. We have logits because we're using BCE with logits loss here. So let's keep pushing forward. We want our accuracy now, which is our accuracy function. And we're going to pass in the order here, which is the reverse of above. A little confusing, but I've kept the evaluation function in the same order as scikit-learn. Ypred equals ypred. 3, we're going to zero the gradients of the optimizer. Optimizer 0 grad. And you might notice that we've started to pick up the pace a little. That is perfectly fine. If I'm typing too fast, you can always slow down the video, or you could just watch what we're doing and then code it out yourself afterwards. The code resources will always be available. We're going to take the loss backward and perform back propagation. The only reason we're going faster is because we've covered these steps. So anything that we sort of spend time here, we've covered in a previous video. Optimizer step, and this is where the adjustments to all of our model's parameters are going to take place to hopefully create a better representation of the data. And then we've got testing. What's the first step that we do in testing? Well, we call model1.eval to put it in evaluation mode. And because we're making predictions, we're going to turn on torch inference mode. Predictions, I call them predictions. Some other places call it inference. Remember, machine learning has a lot of different names for the same thing. Forward pass. So we're going to create the test logits here. Equals model1 x test. And we're going to squeeze them because we don't want the extra one dimension. Just going to add some code cells here so that we have more space, and I'm typing in the middle of the screen. Then I'm going to put in test pred here. How do we get from logits to predictions? Well, we go torch.round, and then we go torch.sigmoid. Why sigmoid? Because we're working with a binary classification problem, and to convert logits from a binary classification problem to prediction probabilities, we use the sigmoid activation function. And then we're going to calculate the loss. So how wrong is our model on the test data? So test lost equals loss function. We're going to pass it in the test logits, and then we're going to pass it in ytest for the ideal labels, and then we're going to also calculate test accuracy. And test accuracy is going to take in ytrue equals ytest, so the test labels, and ypred equals test pred, so the test predictions. Test predictions here. And our final step is to print out what's happening. So print out what's happening. Oh, every tutorial needs a song. If I could, I'd teach everything with song. Song and dance. So because we're training for 1,000 epochs, how about every 100 epochs we print out something? So print F string, and we're going to write epoch in here so we know what epoch our model's on, and then we're going to print out the loss. Of course, this is going to be the training loss because the test loss has test at the front of it, and then the accuracy here. Now, of course, this is going to be the training accuracy. We go here, and then we're going to pipe, and we're going to print out the test loss, and we want the test loss here. We're going to take this to 5 decimal places. Again, when we see the printouts of the different values, do not worry too much about the exact numbers on my screen appearing on your screen, because that is inherent to the randomness of machine learning. So have we got, the direction is more important. Have we got, we need a percentage sign here because that's going to be a bit more complete for accuracy. Have we got any errors here? I don't know. We've just all coded this freehand, right? There's a lot of code going on here. So we're about to train our next model, which is the biggest model we've built so far in this course. 3 layers, 10 hidden units on each layer. Let's see what we've got. 3, 2, 1, run. Oh, what? What? 1,000 epochs, an extra hidden layer, more hidden units, and our model is still basically a coin toss. 50%. Now, this can't be for real. Let's plot the decision boundary. Plot the decision boundary. To find out, let's get a bit visual. Plot figure. Actually, to prevent us from writing out all of the plot code, let's just go up here and we'll copy this. Now, you know I'm not the biggest fan of copying code, but for this case, we've already written it, so there's nothing really new here to cover. And we're going to just change this from model 0 to model 1 because why? It's our new model that we just trained. And so behind the scenes, plot decision boundary is going to make predictions with the target model on the target data set and put it into a nice visual representation for us. Oh, I said nice visual representation. What does this look like? We've just got a coin toss on our data set. Our model is just, again, it's trying to draw a straight line to separate circular data. Now, why is this? Our model is based on linear. Is our data non-linear? Maybe I've revealed a few of my tricks. I've done a couple of reveals over the past few videos, but this is still quite annoying, and it can be fairly annoying when you're training models and they're not working. So how about we verify that this model can learn anything? Because right now it's just basically guessing for our data set. So this model looks a lot like the model we built in section 01. Let's go back to this. This is the Learn pytorch.io book. PyTorch Workflow Fundamentals. Where did we create a model? Model Building Essentials. Where did we build a model? Linear regression model. Yeah, here. nn.linear. But we built this model down here. So all we've changed from 01 to here is we've added a couple of layers. The forward computation is quite similar. If this model can learn something on a straight line, can this model learn something on a straight line? So that's my challenge to you is grab the data set that we created in this previous notebook. So data, you could just reproduce this exact data set and see if you can write some code to fit the model that we built here, this one here, on the data set that we created in here. Because I want to verify that this model can learn anything. Because right now it seems like it's not learning anything at all. And that's quite frustrating. So give that a shot and I'll see you in the next video. Welcome back. In the past few videos, we've tried to build a model to separate the blue from red dots, yet our previous efforts have proven futile. But don't worry, we're going to get there. I promise you we're going to get there. Now, I may have a little bit of inside information here, but we're going to build a model to separate these blue dots from red dots, a fundamental classification model. And we tried a few things in the last couple of videos, such as training for longer, so more epochs. We added another layer. We increased the hidden units because we learned of a few methods to improve a model from a model perspective, such as upgrading the hyperparameters, such as number of layers, more hidden units, fitting for longer, changing the activation functions, changing the learning rate. We haven't quite done that one yet, and changing the loss function. One way that I like to troubleshoot problems is, I'm going to put a subheading here, 5.1. We're going to preparing data to see if our model can fit a straight line. So one way to troubleshoot, this is my trick for troubleshooting problems, especially neural networks, but just machine learning in general. To troubleshoot a larger problem is to test out a smaller problem. And so why is this? Well, because we know that we had something working in a previous section. So 01 PyTorch workflow fundamentals, we built a model here that worked. And if we go right down, we know that this linear model can fit a straight line. So we're going to replicate a data set to fit a straight line to see if the model that we're building here can learn anything at all, because right now it seems like it can't. It's just tossing a coin to split between our data here, which is not ideal. So let's make some data. But yeah, this is let's create a smaller problem, one that we know that works, and then add more complexity to try and solve our larger problem. So create some data. This is going to be the same as Notebook 01. And I'm going to set up weight equals 0.7, bias equals 0.3. We're going to move quite quickly through this because we've seen this in module 1. But the overall takeaway from this is we're going to see if our model works on any kind of problem at all, or do we have something fundamentally wrong. Create data. We're going to call it X regression because it's a straight line and we want it to predict a number rather than a class. So you might be thinking, oh, we might have to change a few things of our model architecture. Well, we'll see that in a second. Dot unsqueeze, and we're going to go on the first dimension here, or dim equals 1. And Y regression, we're going to use the linear regression formula as well. Weight times X. X regression, that is, because we're working with a new data set here, plus the bias. So this is linear regression formula without epsilon. So it's a simplified version of linear regression, but the same formula that we've seen in a previous section. So now let's check the data. Nothing we really haven't covered here, but we're going to do a sanity check on it to make sure that what we're dealing with is not just a load of garbage, because it's all about the data in machine learning. I can't stress to you enough. That's the Data Explorer's motto, is to visualize, visualize, visualize. Oh, what did we get wrong here? Unsqueeze, did you notice that typo? Why didn't you say something? I'm kidding. There we go. Okay, so we've got 100 samples of X. We've got a different step size here, but that's all right. Let's have a little bit of fun with this. And we've got one X value per Y value. This is a very similar data set to what we used before. Now, what do we do once we have a data set? Well, if we haven't already got training and test splits, we better make them. So create train and test splits. And then we're going to go train split. We're going to use 80% equals int 0.8 times the length of, or we could just put 100 in there, but we're going to be specific here. And then we're going to go X train regression, Y train regression equals, what do these equal? Well, we're going to go on X regression and we're going to index up to the train split on the X, and then for the Y regression, we're going to index up to the train split. Wonderful. And then we can do the same on the test, or creating the test data. Nothing really new here that we need to discuss. We're creating training and test sets. What do they do for each of them? Well, the model is going to hopefully learn patterns in the training data set that is able to model the testing data set. And we're going to see that in a second. So if we check the lengths of each, what do we have? Length, xtrain, regression, we might just check xtrain, xtest, regression. What do we have here? And then we're going to go length, ytrain, regression. Long variable names here. Excuse me for that. But we want to keep it separate from our already existing x and y data. What values do we have here? 80, 20, 80, 20. Beautiful. So 80 training samples to 100 testing samples. That should be enough. Now, because we've got our helper functions file here, and if you don't have this, remember we wrote some code up here before to, where is it? To download it from the course GitHub, and we imported plot predictions from it. Now, if we have a look at helperfunctions.py, it contains the plot predictions function that we created in the last section, section 0.1. There we go, plot predictions. So we're just running this exact same function here, or we're about to run it. It's going to save us from retyping out all of this. That's the beauty of having a helperfunctions.py file. So if we come down here, let's plot our data to visually inspect it. Right now it's just numbers on a page, and we're not going to plot really any predictions because we don't have any predictions yet, but we'll pass in the train data is equal to xtrain regression, and then the next one is the train labels, which is equal to ytrain regression, and then we have the test data, which is equal to xtest regression, and then we have the test labels. Now I think this should be labels too. Yeah, there we go. Test regression. I might be proven wrong as we try to run this function. Okay, there we go. So we have some training data and we have some testing data. Now, do you think that our model 1, if we have a look, what's model 1, could fit this data? Does it have the right amount of in and out features? We may have to adjust these slightly. So I'd like you to think about that. Do we have to change the input features to our model for this data set? And do we have to change the out features of our model for this data set? We'll find out in the next video. Welcome back. We're currently working through a little side project here. But really the philosophy of what we're doing, we just created a straight line data set because we know that we've built a model in the past, back in section 01, to fit a straight line data set. And why are we doing this? Well, because the model that we've built so far is not fitting or not working on our circular data set here, on our classification data set. And so one way to troubleshoot a larger problem is to test out a smaller problem first. So later on, if you're working with a big machine learning data set, you'd probably start with a smaller portion of that data set first. Likewise, with a larger machine learning model, instead of starting with a huge model, you'll start with a small model. So we're taking a step back here to see if our model's going to learn anything at all on a straight line data set so that we can improve it for a non-straight line data set. And there's another hint. Oh, we're going to cover it in a second, I promise you. But let's see how now we can adjust model 1 to fit a straight line. And I issued you the question at the end of last video. Do we have to adjust the parameters of model 1 in any way, shape or form to fit this straight line data? And you may have realized, or you may not have, that our model 1 is set up for our classification data, which has 2x input features. Whereas this data, if we go x train regression, how many input features do we have? If we just get the first sample, there's only one value, or maybe we get the first 10. There's only one value per, let's remind ourselves, this is input and output shapes, one of the most fundamental things in machine learning and deep learning. And trust me, I still get this wrong all the time, so that's why I'm harping on about it. We have one feature per one label, so we have to adjust our model slightly. We have to change the in features to be 1 instead of 2. The out features can stay the same because we want one number to come out. So what we're going to do is code up a little bit different version of model 1. So same architecture as model 1. but using nn.sequential. We're going to do the faster way of coding a model here. Let's create model 2 and nn.sequential. The only thing that's going to change is the number of input features. So this will be the exact same code as model 1, and the only difference, as I said, will be features, or in features is 1, and then we'll go out features equals 10. So 10 hidden units in the first layer. And of course, the second layer, the number of features here has to line up with the out features of the previous layer. This one's going to output 10 features as well. So we're scaling things up from 1 feature to 10 to try and give our model as much of a chance or as many parameters as possible. Of course, we could make this number quite large. We could make it 1,000 features if we want. But there is an upper bound on these things. And I'm going to let you find those in your experience as a machine learning engineer and a data scientist. But for now, we're keeping it nice and small so we can run as many experiments as possible. Beautiful, look at that. We've created a sequential model. What happens with nn.sequential? Data goes in here, passes through this layer. Then it passes through this layer. Then it passes through this layer. And what happens when it goes through the layer? It triggers the layer's forward method, the internal forward method. In the case of nn.linear, we've seen it. It's got the linear regression formula. So if we go nn.linear, it performs this mathematical operation, the linear transformation. But we've seen that before. Let's keep pushing forward. Let's create a loss and an optimizer. Loss and optimizer. We're going to work through our workflow. So loss function, we have to adjust this slightly. We're going to use the L1 loss because why? We're dealing with a regression problem here rather than a classification problem. And our optimizer, what can we use for our optimizer? How about we bring in just the exact same optimizer, SGD, that we've been using for our classification data. So model 2.params or parameters. I always get a little bit confused. And we'll give it an LR of 0.1 because that's what we've been using so far. This is the params here. So we want our optimizer to optimize our model 2 parameters here with a learning rate of 0.1. The learning rate is what? The amount each parameter will be, or the multiplier that will be applied to each parameter each epoch. So now, let's train the model. Do you think we could do that in this video? I think we can. So we might just train it on the training data set, and then we can evaluate it on the test data set separately. So we'll set up both manual seeds, CUDA, and because we've set our model to the device up here, so it should be on the GPU or whatever device you have active. So set the number of epochs. How many epochs should we set? Well, we set 1,000 before, so we'll keep it at that. Epochs equals 1,000. And now we're getting really good at this sort of stuff here. Let's put our data, put the data on the target device. And I know we've done a lot of the similar steps before, but there's a reason for that. I've kept all these in here because I'd like you to, by the end of this course, is to sort of know all of this stuff off by heart. And even if you don't know it all off by heart, because trust me, I don't, you know where to look. So X-train regression, we're going to send this to device. And then we're going to go Y-train regression. Just a reminder, or something to get you to think while we're writing this code. What would happen if we didn't put our data on the same device as a model? We've seen that error come up before, but what happens? Well, I've just kind of given away, haven't you, Daniel? Wow, that was a great question. Our code will error. Oh, well, don't worry. There's plenty of questions I've been giving you that I haven't given the answer to yet. Device, beautiful. We've got a device agnostic code for the model and for the data. And now let's loop through epochs. So train, we're going to for epoch in range epochs, for an epoch in a range, do the forward pass, calculate the loss. So ypred equals model 2, this is the forward pass, X-train regression. It's all going to work out hunky-dory because our model and our data are on the same device. Loss equals what? We're going to bring in our loss function. We're going to compare the predictions to Y-train regression, to the Y labels. What do we do next? Optimizer 0 grad. Optimizer.0 grad. We're doing all of this without comments. Look at us go. loss backward, and what's next? Optimize a step, step, step. And of course, we could do some testing here. Testing. We'll go model2.eval, and then we'll go with torch.inference mode. We'll do the forward pass. We'll create the test predictions equals model2.xtest regression. And then we'll go the test loss equals loss fn on the test predictions and versus the y test labels. Beautiful. Look at that. We've just done an optimization loop, something we spent a whole hour on before, maybe even longer, in about 10 lines of code. And of course, we could shorten this by making these a function. But we're going to see that later on. I'd rather us give a little bit of practice while this is still a bit fresh. Print out what's happening. Let's print out what's happening. What should we do? So because we're training for 1,000 epochs, I like the idea of printing out something every 100 epochs. That should be about enough of a step. Epoch, what do we got? We'll put in the epoch here with the F string, and then we'll go to loss, which will be loss, and maybe we'll get the first 5 of those, 5 decimal places that is. We don't have an accuracy, do we? Because we're working with regression. And we'll get the test loss out here, and that's going to be 0.5F as well. Beautiful. Have we got any mistakes? I don't think we do. We didn't even run this code cell before. We'll just run these 3 again, see if we got... Look at that! Oh my goodness, is our loss is going down. So that means our model must be learning something. Now, what if we adjusted the learning rate here? I think if we went 0.01 or something, will that do anything? Oh yes, look how low our loss gets on the test data set, but let's confirm that. We've got to make some predictions. Or maybe we should do that in the next video. Yeah, this one's getting too long, but how good's that? We created a straight line data set, and we've created a model to fit it. We set up a loss and an optimizer already, and we put the data on the target device. We trained and we tested, so our model must be learning something, but I'd like you to give a shot at confirming that by using our plot predictions function. So make some predictions with our trained model. Don't forget to turn on inference mode, and we should see some red dots here, fairly close to the green dots on the next plot. Give that a shot, and I'll see you in the next video. Welcome back. In the last video, we did something very exciting. We solved a smaller problem that's giving us a hint towards our larger problem. So we know that the model that we've previously been building, Model 2, has the capacity to learn something. Now, how did we know that? Well, it's because we created this straight line data set. We replicated the architecture that we used for Model 1. Recall that Model 1 didn't work very well on our classification data, but with a little bit of an adjustment, such as changing the number of in features, and not too much different training code except for a different loss function because, well, we use MAE loss with regression data. And we changed the learning rate slightly because we found that maybe our model could learn a bit better. And again, I'd encourage you to play around with different values of the learning rate. In fact, anything that we've changed, try and change it yourself and just see what happens. That's one of the best ways to learn what goes on with machine learning models. But we trained for the same number of epochs. We set up device agnostic code. We did a training and testing loop. Look how good this looks. Oh my goodness, well done. And our loss went down. So, what does that tell us? Well, it tells us that Model 2, or the specific architecture, has some capacity to learn something. So we must be missing something. And we're going to get to that in a minute, I promise you. But we're just going to confirm that our model has learned something and it's not just numbers on a page going down by getting visual. So turn on, we're going to make some predictions and plot them. And you may have already done this because I issued that challenge at the end of the last video. So turn on evaluation mode. Let's go model2.eval, and let's make predictions, which are also known as inference. And we're going to go with torch.inference mode. Inference mode. With torch.inference mode. Make some predictions. We're going to save them as y preds, and we're going to use model 2, and we're going to pass it through xtest regression. This should all work because we've set up device agnostic code, plot data, and predictions. To do this, we can of course use our plot predictions function that we imported via our helperfunctions.py function. The code for that is just a few cells above if you'd like to check that out. But let's set up the train data here. Train data parameter, which is xtrain regression. And my goodness, Google Colab, I'm already typing fast enough. You don't have to slow me down by giving me the wrong autocorrects. Train label equals ytrain regression. And then we're going to pass in our test data equals xtest regression. And then we're going to pass in test labels, which is ytest regression. We've got too many variables going on here. My goodness gracious. We could have done better with naming, but this will do for now. Is ypreds. And then if we plot this, what does it look like? Oh no, we got an error. Now secretly, I kind of knew that that was coming ahead of time. That's the advantage of being the host of this machine learning cooking show. So type error, how do we fix this? Remember how I asked you in one of the last videos what would happen if our data wasn't on the same device as our model? Well, we'd get an error, right? But this is a little bit different as well. We've seen this one before. We've got CUDA device type tensor to NumPy. Where is this coming from? Well, because our plot predictions function uses matplotlib, and behind the scenes, matplotlib references NumPy, which is another numerical computing library. However, NumPy uses a CPU rather than the GPU. So we have to call .cpu, this helpful message is telling us, call tensor.cpu before we use our tensors with NumPy. So let's just call .cpu on all of our tensor inputs here and see if this solves our problem. Wonderful, looks like it does. Oh my goodness, look at those red dots, so close. Well, okay, so this just confirms our suspicions. What we kind of already knew is that our model did have some capacity to learn. It's just the data set, when we changed the data set, it worked. So, is it our data that our model can't learn on? Like this circular data? Or is it the model itself? Remember, our model is only comprised of linear functions. What is linear? Linear is a straight line, but is our data made of just straight lines? I think it's got some non-linearities in there. So, the big secret I've been holding back will reveal itself starting from the next video. So if you want a head start on it, I'd go to torch3, and if we have a look at the documentation, we've been speaking a lot about linear functions. What are these? Non-linear activations. And I'll give you another spoiler. We've actually seen one of these non-linear activations throughout this notebook. So go and check that out, see what you can infer from that, and I'll see you in the next video. Let's get started with non-linearities. Welcome back. In the last video, we saw that the model that we've been building has some potential to learn. I mean, look at these predictions. You could get a little bit better, of course, get the red dots on top of the green dots, but we're just going to leave that. The trend is what we're after. Our model has some capacity to learn, except this is straight line data. And we've been hinting at it a fair bit, is that we're using linear functions. And if we look up linear data, what does it look like? Well, it has quite a straight line. If we go linear, and just search linear, what does this give us? Linear means straight. There we go, straight. And then what happens if we search for non-linear? I kind of hinted at this as well. Non-linear. Oh, we get some curves. We get curved lines. So linear functions, straight, non-linear functions. Now, this is one of the beautiful things about machine learning. And I'm not sure about you, but when I was in high school, I kind of learned a concept called line of best fit, or y equals mx plus c, or y equals mx plus b, and it looks something like this. And then if you wanted to go over these, you use quadratic functions and a whole bunch of other stuff. But one of the most fundamental things about machine learning is that we build neural networks, and deep down, neural networks are just a combination, it could be a large combination of linear functions and non-linear functions. So that's why in torch.nn we have non-linear activations and we have all these other different types of layers. But essentially what they're doing deep down is combining straight lines with, if we go back up to our data, non-straight lines. So of course our model didn't work before Because we've only given it the power to use linear lines. We've only given it the power to use straight lines. But our data is what? It's curved. Although it's simple, we need non-linearity to be able to model this data set. And now, let's say we were building a pizza detection model. So let's look up some images of pizza, one of my favorite foods. Images. Pizza, right? So could you model pizza with just straight lines? Now you're thinking, Daniel, you can't be serious. A computer vision model doesn't look for just straight lines in this. And I'd argue that, yes, it does, except we also add some curved lines in here. That's the beauty of machine learning. Could you imagine trying to write the rules of an algorithm to detect that this is a pizza? Maybe you could put in, oh, it's a curve here, and if you see red and... No. Imagine if you're trying to do 100 different foods. Your program would get really large. Instead, we give our machine learning models, if we come down to the model that we created, we give our deep learning models the capacity to use linear and non-linear functions. We haven't seen any non-linear layers just yet. Or maybe we've hinted at some, but that's all right. So we stack these on top of each other, these layers, and then the model figures out what patterns in the data it should use, what lines it should draw to draw patterns through not only pizza, but another food such as sushi. If we wanted to build a food image classification model, it would do this. The principle remains the same. So the question I'm going to pose to you, we'll get out of this, is we'll come down here. We've unlocked the missing piece, or we're about to. We're going to cover it over the next couple of videos. The missing piece of our model. And this is a big one. This is going to follow you out throughout all of machine learning and deep learning. Non-linearity. So the question here is, what patterns could you draw if you were given an infinite amount of straight and non-straight lines? Or in machine learning terms, an infinite amount, but really it is finite. By infinite, in machine learning terms, this is a technicality. It could be 1,000,000 parameters. It could be, as we've got, probably 100 parameters in our model. So just imagine a large amount of straight and non-straight lines, an infinite amount of linear and non-linear functions. You could draw some pretty intricate patterns, couldn't you? And that's what gives machine learning, and especially neural networks, the capacity to not only fit a straight line here, but to separate two different circles, but also to do crazy things like drive a self-driving car, or at least power the vision system of a self-driving car. Of course, after that, you need some programming to plan what to actually do with what you see in an image. But we're getting ahead of ourselves here. Let's now start diving into non-linearity. And the whole idea here is combining the power of linear and non-linear functions. Straight lines and non-straight lines. Our classification data is not comprised of just straight lines, it's circles. So we need non-linearity here. So recreating non-linear data, red and blue circles. We don't need to recreate this, but we're going to do it anyway for completeness. So let's get a little bit of a practice. Make and plot data. This is so that you can practice the use of nonlinearity on your own. Matplotlib.pyplot as PLT. We're going to go a bit faster here because we've covered this code above. So import make circles. We're just going to recreate the exact same circle data set that we've created above. Number of samples, we'll create 1,000. And we're going to create x and y equals what? Make circles, pass it in number of samples. Beautiful. Colab, please. I wonder if I can turn off autocorrect on Colab. I'm happy to just see all of my errors in the flesh. See, look at that. I don't want that. I want noise like that. Maybe I'll do that in the next video. We're not going to spend time here looking around how to do it. We can work that out on the fly later. For now, I'm too excited to share with you the power of nonlinearity. So here, X, we're just going to plot what's going on. We've got two X features, and we're going to color it with the flavor of Y, because we're doing a binary classification. And we're going to use one of my favorite CMaps, which is color map, and we're going to go plt.cm for CMap and red, blue. What do we get? Okay, red circle, blue circle. Hey, is that the same color as what's above? I like this color better. Did we get that right up here? Oh my goodness, look how much code we've written. Yeah, I like the other blue. I'm going to bring this down here. It's all about aesthetics and machine learning. It's not just numbers on a page. Daniel, how could you be so crass? Let's go there. Okay, that's a better color, red and blue. That's more lively, isn't it? So now let's convert to train and test, and then we can start to build a model with nonlinearity. Oh, this is so good. Okay, convert data to tensors, and then to train and test splits. Nothing we haven't covered here before. So import torch, but it never hurts to practice code, right? Import torch from sklearn.model selection. Import train test split so that we can split our red and blue dots randomly. And we're going to turn data into tensors. And we'll go x equals torch from numpy, and we'll pass in x here. And then we'll change it into type torch.float. Why do we do this? Well, because, oh my goodness, autocorrect. It's getting the best of me here. You're watching me live code this stuff and battle with autocorrect. That's what this whole course is. Am I really teaching PyTorch, or am I just battling with Google Colab's autocorrect? We are turning it into torch.float with a type here because, why? NumPy's default, which is what Make Circles uses behind the scenes. NumPy is actually used in a lot of other machine learning libraries. Pandas, built on NumPy. Scikit-learn does a lot of NumPy. Matplotlib, NumPy. That's just showing the, what's the word? Is it ubiquitous? Ubiquity? I'm not sure, maybe. If not, you can correct me. The ubiquity of NumPy and test sets, but we're using PyTorch to leverage the power of autograd, which is what powers our gradient descent, and the fact that it can use GPUs. So we're creating train and test splits here with train test split x, y, and we're going to go test size equals 0.2, and we're going to set random state equals 42, and then we'll view our first 5 samples. Are these going to be tensors? Fingers crossed, we haven't got an error. Beautiful, we have tensors here. Okay, now we're up to the exciting part. We've got our data set back. I think it's time to build a model with nonlinearity. So if you'd like to peek ahead, check out TorchNN again. This is a little bit of a spoiler. Go into the nonlinear activations, see if you can find the one that we've already used. That's your challenge. Can you find the one we've already used? And go into here and search what is a nonlinear function. So give that a go and see what comes up. I'll see you in the next video. Welcome back. Now, put your hand up if you're ready to learn about nonlinearity. And I know I can't see your hands up, but I better see some hands up, or I better feel some hands up, because my hand's up, because nonlinearity is a magic piece of the puzzle that we're about to learn about. So let's title this section, Building a Model with Nonlinearity. So just to re-emphasize, linear equals straight lines, and in turn, nonlinear equals non-straight lines. And I left off the end of the last video giving you the challenge of checking out the torch.nn module, looking for the nonlinear function that we've already used. Now, where would you go to find such a thing? And oh, what do we have in here? Nonlinear activations. And there's going to be a fair few things here, but essentially all of the modules within torch.nn are either some form of layer in a neural network, if we recall. Let's go to a neural network. We've seen the anatomy of a neural network. Generally, you'll have an input layer and then multiple hidden layers and some form of output layer. Well, these multiple hidden layers can be almost any combination of what's in torch.nn. And in fact, they can almost be any combination of function you could imagine. Whether they work or not is another question. But PyTorch implements some of the most common layers that you would have as hidden layers, and they might be pooling layers, padding layers, activation functions, and they all have the same premise.